Welcome to State of the AI Industry 2025, your essential guide to understanding one of the most transformative technological revolutions of our time. I'm Stephen, and this is our inaugural episode, where we begin an ambitious journey through the intricate layers of artificial intelligence. For tech professionals, entrepreneurs, and anyone seeking to understand how AI is reshaping our world, this podcast offers a structured exploration of the multifaceted ecosystem that's emerging before our eyes.
And I'm Edith. Today marks the beginning of our comprehensive tour through the AI landscape, where we'll break down this complex industry into digestible segments. Each episode focuses on a distinct layer of the AI ecosystem, from the foundational hardware that powers these systems to the cutting-edge research labs pushing the boundaries of what's possible, and eventually to the applications transforming entire industries.
The AI industry presents a fascinating paradox. On one hand, we're witnessing unprecedented growth and innovation. The global AI market reached over $638 billion in 2025 and is projected to exceed $3.6 trillion by 2034. Yet beneath these staggering numbers lies a complex web of interconnected segments, each with its own dynamics, challenges, and opportunities. The question isn't whether AI will transform industries, it already has. The question is how to navigate this transformation intelligently.
Exactly. And that's where understanding the market map becomes crucial. In today's episode, we're laying the foundation by examining 6 key segments that define the AI value chain: foundation models, AI infrastructure, model tooling and orchestration, agentic automation platforms, vertical applications, and services and system integrators. Each segment plays a critical role, and understanding their relationships is essential for anyone building, investing in, or implementing AI solutions.
What makes this landscape particularly intriguing is how these segments interact and depend on each other. Foundation models require massive computational infrastructure. That infrastructure needs sophisticated tooling to manage and orchestrate. Those tools enable the creation of autonomous agents. Agents power specific vertical applications, and services tie it all together for enterprise adoption. It's a delicate ecosystem where changes in one segment ripple through all others.
Let's start at the foundation, literally. The foundation model segment represents the core intelligence layer of the AI stack. These are the large language models, multimodal systems, and specialized models that capture human-like reasoning capabilities. We're talking about OpenAI's GPT series, Anthropic's Claude, Google's Gemini, and emerging players like Mistral and xAI. This segment is currently valued in the low tens of billions, but growing rapidly as enterprise adoption accelerates.
What's remarkable about foundation models is how quickly the competitive landscape has evolved. Just 2 years ago, OpenAI dominated enterprise usage with a 50% market share. Today, Anthropic has captured 32% of enterprise usage, particularly excelling in coding applications with 42% market share. This shift highlights how rapidly capabilities and preferences can change in this space.
The economics of foundation models are fascinating. These companies monetize through APIs, enterprise licenses, and consumer subscriptions. Anthropic, for instance, generated around $950 million in revenue last year, with 2/3 coming from API calls. They've now reached $2 billion in annualized revenue and could hit $4 billion by year's end. The constraint here isn't demand, it's compute cost and safety considerations.
That constraint brings us naturally to the second segment, AI infrastructure. This is where the rubber meets the road in terms of raw computational power. We're looking at GPUs, TPUs, specialized AI chips, networking equipment, memory systems, and the cloud services that make them accessible. NVIDIA dominates this space, but we're seeing fierce competition from AMD, Intel, and cloud providers like AWS, Google Cloud, and Microsoft Azure. Think of AI infrastructure as the power grid for artificial intelligence. Just as electricity transformed industry in the early 1900s, AI infrastructure is the enabling layer for this transformation. The numbers are staggering. Between $3 and $4 trillion will be spent on AI infrastructure by the end of this decade, according to NVIDIA's CEO Jensen Huang. In the first half of 2024 alone, organizations increased AI infrastructure spending by 97% year over year, reaching $47.4 billion. The infrastructure segment faces unique challenges. Supply constraints are constant, with leading-edge chips in perpetual shortage. Energy consumption is becoming a critical bottleneck. Modern AI data centers can require 40 kilowatts per rack, necessitating liquid cooling systems and massive power infrastructure investments. These constraints create interesting dynamics where cloud GPU services have emerged as a critical bridge, allowing organizations to access cutting-edge hardware without massive capital expenditures.
Now, having powerful models and infrastructure isn't enough. You need sophisticated tools to manage them effectively. This brings us to our third segment, model tooling and orchestration. This includes frameworks for fine-tuning models, retrieval-augmented generation systems, evaluation platforms, safety monitoring, and optimization tools. It's a fragmented but rapidly growing space, with players like Hugging Face, Weights and Bias, and LangChain leading different aspects.
The tooling segment is particularly interesting because it sits at the intersection of technical capability and operational necessity. As AI systems become more complex and move into production environments, organizations need robust frameworks for monitoring performance, ensuring safety, and managing model lifecycle. Weights and Biases, for example, provides end-to-end AI oversight, helping organizations track everything from initial experiments to production deployment. What's emerging here is a recognition that building AI applications isn't just about having access to powerful models, it's about having the entire supporting ecosystem. LangChain and Llama Index have become the de facto orchestration frameworks, with LangChain focusing on complex multi-step workflows and Llama Index excelling at data-centric retrieval applications. These tools are abstractions that make AI development more accessible and reliable.
This foundation of models, infrastructure, and tooling enables our fourth segment, agentic automation platforms. This is where AI transitions from reactive systems that respond to prompts to proactive agents that can autonomously complete complex workflows. Salesforce's Agent Force, Microsoft's Copilot Agent Mode, and emerging frameworks like AutoGPT represent different approaches to this challenge.
Agentic systems represent perhaps the most exciting frontier in AI today. Instead of just answering questions, these systems can take action, make decisions, and complete multi-step tasks with minimal human intervention. Salesforce's Agent Force has already handled over 750,000 customer service requests autonomously, resolving 84% of inquiries without human intervention. The platform has generated over 8,000 deals and $100 million in annual order value within months of launch.
The agentic market is projected to grow from about $7 billion in 2025 to over $42 billion by 2030. That's a compound annual growth rate of over 43%. But this segment faces unique challenges around reliability, safety, and trust. When an AI system is just providing information, mistakes are correctable. When it's taking autonomous actions, the stakes are much higher.
Which brings us to our fifth segment, vertical applications. This is where AI capabilities meet specific industry needs. Think GitHub Copilot revolutionizing software development, Harvey AI transforming legal research, or specialized diagnostic tools in healthcare. This segment is experiencing the fastest growth because it delivers immediate, measurable value to end users.
Vertical AI represents the largest opportunity in terms of total addressable market. The global healthcare AI market alone has grown 233% between 2020 and 2023, from $6.7 billion to $22.4 billion. Legal AI is projected to grow from $1.9 billion in 2024 to $3.9 billion by 2030. Each vertical has unique requirements, regulatory considerations, and value propositions.
GitHub Copilot provides an excellent case study for vertical AI success. It now has over 20 million all-time users and is used by 90% of Fortune 100 companies. The platform has grown 75% quarter over quarter in enterprise usage. What's particularly interesting is how it spawned an entire ecosystem of AI coding tools, with companies like Cursor achieving $500 million in annual recurring revenue and attracting over 1 million daily users.
Finally, we have our sixth segment, services, system integrators, and go-to-market channels. This includes consulting firms like Accenture, IBM, and Deloitte, as well as specialized AI agencies that help enterprises implement and scale AI solutions. This segment is critical because it bridges the gap between AI capabilities and real-world business outcomes.
The AI consulting services market is experiencing explosive growth, expanding from $8.75 billion in 2024 to a projected $49 billion by 2032. That's a compound annual growth rate of over 24%. Accenture alone has generated $1.5 billion in generative AI bookings, and the firm recently restructured into a new reinventions unit specifically focused on AI-powered transformations. What's driving this growth is a fundamental skills gap. Organizations recognize the transformative potential of AI, but they lack the internal expertise to implement it effectively. System integrators provide the strategic guidance, technical implementation, and ongoing support necessary to turn AI investments into business results. The constraint here isn't market demand, it's the availability of skilled AI talent.
Let's step back and connect these segments. Imagine the AI value chain as a complex supply chain. Foundation models are the core product, requiring massive infrastructure to produce and serve. Tooling and orchestration provide the manufacturing and quality control processes. Agentic platforms are the distribution mechanisms that make AI capabilities more accessible. Vertical applications are the final products that consumers actually use. And services are the retail and support layer that makes everything work in practice.
This interconnectedness creates interesting dynamics. For instance, when Anthropic's Claude 3.5 Sonnet delivered superior coding capabilities, it didn't just affect the foundation model segment. It rippled through to coding-focused vertical applications, influenced tooling choices, and created new opportunities for system integrators specializing in developer tools. Similarly, advances in GPU architecture affect model training costs, which influence pricing strategies across all downstream segments.
The growth patterns across segments are also revealing. Infrastructure and foundation models are capital-intensive but have the potential for massive scale economies. Tooling and orchestration benefit from network effects as more developers adopt standardized frameworks. Agentic platforms are still nascent but growing rapidly as reliability improves. Vertical applications have the clearest path to revenue but face the challenge of achieving sufficient scale. Services grow with overall market adoption but require continuous investment in talent and capabilities.
From an investment perspective, each segment presents different risk-reward profiles. Foundation models require enormous capital but can achieve unprecedented scale. Infrastructure plays benefit from being essential to the entire ecosystem. Tooling companies can achieve high margins by solving critical pain points. Agentic platforms are high-risk, high-reward bets on the future of work. Vertical applications offer clearer paths to profitability but may face competition from horizontal solutions. Services firms benefit from immediate market demand but face margin pressure from commoditization.
Looking at constraints across segments, we see common themes emerging. Compute cost affects everyone, from foundation model providers to vertical application developers. Talent shortages are particularly acute in specialized areas like AI safety and ML ops. Regulatory uncertainty creates challenges for autonomous systems and data-sensitive applications. And perhaps most importantly, the integration complexity of bringing together solutions from multiple segments often becomes the bottleneck for enterprise adoption.
These constraints also create opportunities. Companies that can reduce compute costs through efficiency gains capture value across the ecosystem. Platforms that simplify integration and reduce implementation complexity have massive market potential. Solutions that address safety and regulatory requirements become essential for enterprise adoption. And organizations that can effectively combine capabilities from multiple segments can create significant competitive advantages.
As we wrap up today's market mapping exercise, the key insight is that the AI industry isn't a monolithic entity. It's a complex ecosystem where success depends on understanding the interplay between segments. Each segment has its own growth drivers, constraints, and success factors, but they're all interconnected, creating both challenges and opportunities for organizations operating within this ecosystem.
The AI market spans from fundamental research to practical applications, from massive infrastructure investments to specialized consulting services. Enterprise demand and cloud distribution are driving growth across all segments, while compute costs and safety considerations remain universal constraints. Understanding this map isn't just academic, it's essential for making informed decisions about where to build, invest, or implement AI solutions.
In our next episode, we'll dive deep into the strategies of major technology companies as they position themselves across these segments. We'll examine how Microsoft is integrating OpenAI models across its entire product suite, how Amazon is balancing in-house development with partnerships, how Google is leveraging its data advantages, and how newer players like Salesforce are creating entirely new categories around agentic AI. The competitive dynamics we'll explore show how understanding this market map translates into real-world strategy.
Until then, remember that the AI revolution isn't happening in isolation. It's happening through the complex interplay of these 6 segments. Whether you're building the next breakthrough model, investing in AI infrastructure, or implementing solutions for your organization, success depends on understanding how these pieces fit together. Thanks for joining us on State of the AI Industry 2025.
The future of AI is being built right now across every segment we've discussed today. See you next time as we continue mapping the landscape that's shaping tomorrow's world.
Welcome to State of the AI Industry 2025. I'm Steven, and today we're diving deep into one of the most fascinating aspects of our modern AI revolution: how the world's biggest technology companies are not just adopting artificial intelligence, but fundamentally reshaping their entire business strategies around it. What we're witnessing isn't merely the integration of AI into existing products, it's the complete reimagining of corporate DNA.
That's exactly right. And what makes this particularly intriguing is how each of these tech giants is taking radically different approaches to AI dominance. We have Microsoft going all in on their OpenAI partnership while simultaneously building escape hatches, Amazon betting on custom silicon and open ecosystems, Google leveraging its decades of AI research with TPUs and Gemini, and companies like Meta open sourcing their way to relevance. Today, we'll examine Microsoft's AI-centric transformation, Amazon's 3-layer infrastructure play, Google's comprehensive AI platform strategy, Meta's open-source gambit with Llama, Salesforce's agent-first CRM revolution, Adobe's creator-focused AI integration, Apple's privacy-first on-device intelligence, and how Oracle, Databricks, and Snowflake are positioning themselves in this new landscape.
What's fascinating is that we're seeing these strategies emerge just as our previous episode explored the market segments and value chain. The foundation models, AI infrastructure, tooling, and vertical applications we discussed are now becoming the battlegrounds where these companies are fighting for supremacy. But here's the critical insight. Each company's approach reveals not just their AI ambitions, but their fundamental understanding of where value will be captured in the next decade.
Think of it like a massive chess game, where every player has chosen a completely different opening strategy. Microsoft is playing the partnership gambit. They've invested over $13 billion in OpenAI to secure access to cutting-edge models. But they're also quietly developing their own pieces as insurance. It's like having a brilliant chess partner who might leave the tournament halfway through, so you're simultaneously learning their moves while training to play solo.
That analogy perfectly captures Microsoft's strategic tension. Their Azure infrastructure has become the training ground for GPT models, and they've embedded OpenAI's technology across their entire ecosystem, from Microsoft 365 Copilot to GitHub Copilot to Azure OpenAI Service. But reports suggest cracks are showing in this partnership. Microsoft has been quietly testing its own MAI-1 preview model and integrating Anthropic's Claude into their Copilot platform. They're essentially hedging their bets while maximizing their current advantage.
What makes Microsoft's strategy so compelling is how they're using AI to reinforce their existing moats. They're not just adding AI features, they're making AI the connective tissue that binds users deeper into their ecosystem. When you use Copilot across Word, Excel, PowerPoint, and Teams, switching costs become exponentially higher because the AI learns your patterns across all these applications. It's like having a personal assistant who knows all your preferences, workflows, and colleagues. Replacing that becomes almost unthinkable.
Amazon Web Services is taking a fundamentally different approach with their three-layer strategy. At the bottom layer, they're betting heavily on custom silicon with Trainium for training and Infernia for inference, trying to break free from what they see as the NVIDIA tax. The middle layer focuses on managed services like Amazon Bedrock, which provides access to multiple foundation models through a single API. And the top layer includes applications like Amazon Q, their enterprise AI assistant.
Amazon's strategy reminds me of a hardware store that decides to manufacture its own tools. They looked at their massive cloud infrastructure bills to NVIDIA and said, we can build this ourselves, better and cheaper. Their Trainium and Infernia chips are designed specifically for AI workloads, promising up to 50% lower training costs compared to traditional GPUs. But here's the challenge. Most AI developers are deeply entrenched in NVIDIA's CUDA ecosystem. Amazon is essentially asking the entire industry to learn new tools when the old ones work perfectly well.
The Anthropic's partnership adds another fascinating dimension to Amazon's strategy. They've invested up to $4 billion in Anthropic, making AWS their primary cloud provider. This gives Amazon access to cutting-edge models while providing Anthropic with the infrastructure they need to compete with OpenAI. It's a symbiotic relationship where Amazon gets to participate in the foundation model race without having to build those capabilities entirely from scratch.
Google's approach is perhaps the most comprehensive because they're playing on every level simultaneously. They have their own custom hardware with the new Ironwood TPUs, which deliver up to 24 times more compute than current supercomputers. They have their own foundation models with the Gemini series, including the new Gemini 2.5 that's topping global benchmarks. And they have massive distribution through Search, Workspace, Android, and Google Cloud. It's like they're not just playing chess, they're manufacturing the board, the pieces, and writing the rules.
What's particularly interesting about Google's strategy is how their 20 years of AI investment are now paying dividends. Their TPU advantage isn't just about hardware performance. It's about the entire software stack that's been optimized for their specific use cases. When you can operate AI capabilities for approximately 20% less cost than competitors relying on NVIDIA GPUs, that becomes a massive competitive advantage, especially at scale.
Meta's strategy with Llama is perhaps the most counterintuitive, but it might be the most brilliant. By open sourcing their models, Llama has been downloaded over 1 billion times. They're essentially commoditizing the foundation model layer. It's like a restaurant chef sharing their secret recipes with everyone, but keeping control of the best ingredients and the prime real estate where people want to eat.
The strategic logic behind Meta's open-source approach is fascinating. They're not making money directly from AI models, so giving them away for free doesn't hurt their revenue. But it does undermine competitors like OpenAI and Anthropic who are trying to monetize model access. Meanwhile, Meta gets massive community feedback to improve their models, attracts top AI talent who want to work on open systems, and creates switching costs for the billions of users on their platforms who become accustomed to AI-enhanced Facebook, Instagram, and WhatsApp experiences.
Think of Salesforce's strategy as turning their CRM into an AI-powered autopilot system. With Agentforce, they're not just adding AI features to existing workflows, they're creating autonomous agents that can handle entire customer interactions from start to finish. It's like upgrading from a car with cruise control to one with full self-driving capability. The agents can qualify leads, handle customer service inquiries, process sales transactions, and even manage IT service requests without human intervention.
What makes Salesforce's approach particularly compelling is how they're leveraging their unique position as the system of record for customer relationships. They have access to decades of sales, marketing, and service data across thousands of companies. This gives their AI agents context that generic models simply can't match. When an Agentforce agent handles a customer inquiry, it understands not just the question, but the customer's history, preferences, and value to the business.
Adobe's strategy is beautifully tailored to their core constituency, creative professionals who need AI that enhances rather than replaces human creativity. Their dual-engine approach with Sensei for workflow optimization and Firefly for content generation creates what I call creative amplification. Sensei handles the tedious tasks like background removal and object selection, while Firefly helps generate initial concepts and variations. It's like having a skilled assistant who can handle both the boring technical work and brainstorm creative ideas alongside you.
The commercial safety aspect of Adobe's Firefly models addresses one of the biggest concerns for enterprise creative teams: legal liability. While other generative AI systems might inadvertently use copyrighted material in their training data, Firefly is trained on Adobe stock images and other commercially cleared content. This gives creative professionals confidence that their AI-generated assets won't create legal complications down the road.
Apple's approach represents a fundamental philosophical difference about where AI should live and how privacy should be protected. While everyone else is building massive cloud-based AI systems, Apple is pushing intelligence to the edge, directly onto your iPhone, iPad, and Mac. It's like the difference between having a conversation with someone over a monitored phone line versus speaking face-to-face in a private room.
The technical implementation of Apple Intelligence reveals the sophistication of their approach. Most AI processing happens on-device, using their neural engine chips, which means your personal data never leaves your device. For more complex requests that require larger models, they use private cloud compute, custom Apple Silicon servers where data is processed but never stored. And they give users explicit control over when external services like ChatGPT are used, with full transparency about data handling.
The strategic logic behind Oracle's strategy is fascinating because they're not trying to beat Amazon, Microsoft, or Google at their own game. Instead, they're focusing on the highest value, most regulated customers who need AI but can't compromise on data sovereignty. Their approach is like building a luxury, ultra-secure private club while others are creating massive public venues. Government agencies, financial institutions, and healthcare organizations that need AI capabilities but have strict data residency requirements find Oracle's sovereign cloud offerings compelling.
The depth of AI integration into Oracle's Fusion Cloud applications is impressive. They're not just adding chatbots, they're embedding intelligent agents throughout finance, HR, and supply chain workflows. An AI agent can process supplier invoices, predict cash flow, identify early payment discounts, and even help resolve revenue variances before quarter-end closing. It's AI that's designed specifically for the mission-critical business processes that run large enterprises.
The battle between Databricks and Snowflake illustrates two different visions for how data and AI should work together. Snowflake is saying, bring your data to our optimized environment, and we'll make AI simple. Databricks is saying, keep your data wherever it is, and we'll bring flexible AI tools to you. It's like choosing between a fully equipped professional kitchen where everything is in its place versus a mobile cooking setup that can work anywhere but requires more setup.
What's particularly interesting is how both companies are converging on similar AI capabilities despite their different architectural philosophies. Snowflake's new Cortex AI features let you query data using natural language and embed AI functions directly into SQL. Databricks' AgentBricks framework lets you build custom AI agents just by describing what you want them to do. Both are recognizing that the future of data work involves conversational interfaces and autonomous agents.
Looking at these strategies collectively, we can see several meta patterns emerging. First is the platform versus point solution divide. Companies like Microsoft, Google, and Amazon are building comprehensive AI platforms, while others like Adobe and Salesforce are creating deep vertical solutions. Second is the openness versus control spectrum. Meta is radically open with Llama, Apple is completely closed but privacy-focused, and everyone else is somewhere in between.
The third pattern is about data and distribution advantages. Every successful AI strategy leverages some form of proprietary data or unique access to users. Microsoft has enterprise workflows, Google has search and web data, Meta has social interactions, Salesforce has business relationships, Adobe has creative assets, and Apple has intimate device usage patterns. The companies that can combine powerful AI capabilities with irreplaceable data advantages are the ones positioned for long-term success.
What's most remarkable is that despite all these different strategies, there's room for multiple winners because the AI market is expanding so rapidly. A Salesforce customer using Agentforce might also be using Microsoft's GitHub Copilot for development, Google's Gemini for research, Adobe's Firefly for creative work, and Apple Intelligence on their mobile devices. The question isn't who will win everything, it's who will capture the most valuable segments.
As we look toward our next episode on the compute and hardware landscape, we'll see how these strategic choices by software companies are driving massive infrastructure investments. The companies we've discussed today are collectively spending hundreds of billions of dollars on data centers, custom chips, and cloud infrastructure to support their AI ambitions. The battle for AI dominance isn't just being fought in software. It's reshaping the entire technology stack, from silicon to user interface.
That hardware foundation is absolutely critical because all these beautiful AI strategies we've discussed today mean nothing if you can't deliver the compute performance that users expect. Whether it's Microsoft's Azure infrastructure training GPT models, Google's TPU supercomputers powering Gemini, or Apple's neural engines enabling on-device intelligence, the silicon choices these companies make will determine which strategies actually succeed in the market.
Next time, we'll dive deep into the chip wars between NVIDIA, AMD, Intel, and the growing ecosystem of specialized AI processors. We'll explore how cloud infrastructure is evolving to support these massive AI workloads and examine the supply chain dynamics that could make or break these corporate strategies we've analyzed today. Welcome to State of the AI Industry 2025, where we break down the complex layers that make modern artificial intelligence possible. I'm Stephen, and as we continue our journey through the AI ecosystem, today we're diving deep into one of the most critical yet often overlooked foundations of this entire industry, the compute and hardware landscape that powers everything we've been discussing.
And I'm Edith. You know, if AI models are the brilliant minds we've been exploring, then today's topic is about the physical brains that make thinking possible. We've looked at how big tech companies are strategically positioning themselves in this space, but none of their ambitious AI initiatives would matter without the silicon underneath making it all happen.
Exactly. Think about it. Every ChatGPT query, every image generated by Midjourney, every autonomous vehicle decision, it all comes down to billions of calculations happening on specialized hardware. But here's what makes this particularly fascinating in 2025. We're witnessing a dramatic shift in the hardware landscape that's reshaping not just performance, but the entire economics of AI deployment.
Today, we're going to explore the key players dominating this space, from NVIDIA's continued supremacy with their Blackwell architecture to AMD's aggressive push with their MI300 and MI350 series. We'll examine specialized processors from companies like Grok and Cerebras that are taking radically different approaches. And we'll dive into how supply constraints that plagued the industry are finally starting to ease, creating new strategic opportunities for organizations.
What makes this episode essential is understanding how these hardware decisions ripple through everything else we'll discuss in future episodes. The choice between cloud and on-premise deployment, the economics of running frontier AI models, even which companies can afford to compete at the highest levels. It all starts with silicon. We're not just talking about faster chips, we're talking about the fundamental infrastructure that determines who gets to participate in the AI revolution.
And unlike previous technology waves where hardware was somewhat commoditized, AI has created this incredible specialization where the right chip architecture can mean the difference between a model running in real time or taking minutes to respond. So let's start where any discussion of AI hardware must begin, with the undisputed heavyweight champion.
NVIDIA has achieved something remarkable in the AI era. They've managed to maintain not just market leadership, but what many consider a genuine technological moat. Their latest Blackwell series, particularly the B100 and B200 GPUs, represents a quantum leap in performance. The numbers are staggering. The B200 offers 57% faster training performance compared to the H100, while delivering up to 18 petaflops of compute at FP4 precision.
But here's what's really interesting about NVIDIA's dominance. It's not just about raw performance. Think of NVIDIA like the architect who didn't just design the most beautiful building, but also created the entire city planning system, the construction standards, and trained all the construction workers. Their CUDA ecosystem has become the de facto standard for AI development, meaning that switching to a competitor isn't just about buying different hardware, it's about rewriting years of optimized code.
The Blackwell architecture itself represents a fascinating engineering achievement. We're looking at chips with over 200 billion transistors packed into a dual die design connected by their NVHBI technology. Each B200 comes with 192 gigabytes of HBM3E memory and 8 terabytes per second of memory bandwidth. But the real breakthrough is in their networking. The 5th generation NVLink delivers 1.8 terabytes per GPU, which means these chips can work together almost as if they were a single massive processor.
That networking capability is crucial because modern AI workloads don't run on single chips. They run on clusters of hundreds or thousands of GPUs working in concert. Imagine trying to coordinate a symphony where every musician is in a different building across the city. The communication delays would make beautiful music impossible. NVIDIA's NVLink is like having all those musicians in the same concert hall with perfect acoustics. The coordination becomes seamless.
But here's where the competitive landscape gets interesting. AMD has been making significant strides with their CDNA architecture, and their latest MI3025 and upcoming MI35X chips are genuinely competitive. The MI35X, launching in mid-2025, offers 288 gigabytes of HBM3E memory. That's 50% more than NVIDIA's B200, and delivers comparable performance at FP8 and FP4 precisions that are becoming standard for inference workloads.
AMD's strategy is particularly clever. Instead of trying to beat NVIDIA at their own game, they're focusing on specific advantages. Think of it like a chess match, where AMD isn't trying to replicate NVIDIA's opening strategy, but instead developing their own unique position. Their chips excel in memory-intensive workloads, and they're being adopted by major players like Meta, AWS, and even OpenAI for specific use cases where that extra memory capacity provides tangible benefits.
The timing of AMD's MI355X launch is also strategic. Originally planned for the second half of 2025, they moved it up to mid-year specifically to compete against NVIDIA's Blackwell rollout. The MI355X delivers 1.8 times the performance of the MI325X while featuring new support for FP6 and FP4 data types, achieving up to 10.1 petaflops at FP8 precision. What's particularly noteworthy is their ROCm 7.0 software stack, which showed a 3.5x inference performance improvement, suggesting AMD is finally addressing their software ecosystem gap.
And then we have Intel making waves with their Gaudi 3 architecture. Intel's approach is different. They're betting on Ethernet-based networking instead of proprietary interconnects, and they're targeting what you might call the pragmatic enterprise segment. Their Gaudi 3 PCI cards became available in the second half of 2025, and early benchmarks suggest 70% better price performance than NVIDIA's H100 for specific inference workloads.
Intel's partnership with Dell is particularly interesting here. Dell was first to market with Gaudi 3 systems, and they're positioning this as an alternative to the NVIDIA ecosystem that avoids vendor lock-in. For enterprises that want high-performance AI without committing entirely to CUDA, Gaudi 3 provides a viable path forward, especially for inference-heavy workloads, where the networking requirements are less demanding than in training scenarios.
But let's talk about the truly revolutionary approaches, companies like Grok and Cerebras that are rethinking the fundamental architecture of AI chips. Grok has developed what they call language processing units, or LPUs, which are purpose-built for inference workloads. Instead of trying to be general-purpose like GPUs, LPUs eliminate many of the bottlenecks that create latency in traditional architectures.
Grok's approach is fascinating from a systems design perspective. Their LPU architecture co-locates compute and memory on the chip, eliminating the external memory bottlenecks that plague GPU architectures. They've achieved inference speeds that are genuinely impressive. We're seeing reports of Llama 3.3 70B running at over 1,500 tokens per second. For applications where response time is critical, this represents a paradigm shift in what's possible.
Think of the difference like this. Traditional GPUs are like incredibly powerful freight trains. They can carry enormous loads and process massive amounts of data, but they need time to build up speed and momentum. Grok's LPUs are like high-performance race cars. They're designed specifically for speed and can accelerate instantly. For applications like real-time conversation, code completion, or interactive AI assistance, that instant responsiveness changes the entire user experience.
Cerebras takes the opposite extreme approach with their wafer-scale engine. Instead of making chips smaller and more efficient, they keep the entire silicon wafer as one massive chip. Their WSE3 contains an almost incomprehensible 4 trillion transistors, 900,000 AI-optimized cores, and 44 gigabytes of on-chip SRAM. This isn't just a bigger chip, it's a completely different philosophy of computation.
The Cerebras approach is like the difference between building a city with millions of small apartments connected by roads and bridges versus building one enormous mansion where every room is directly connected to every other room. Traditional GPU clusters spend enormous amounts of power and complexity on interconnects, moving data between chips, coordinating memory access, managing network traffic. Cerebras eliminates all of that by keeping everything on one piece of silicon.
The performance implications are substantial. The WSE3 achieves 125 petaflops of AI compute and 21 petabytes per second of memory bandwidth. But perhaps more importantly, it can handle models with up to 24 trillion parameters natively, without the complex model parallelism strategies that traditional clusters require. For training the largest language models, this architectural approach may represent the future of AI hardware.
Now, we can't discuss the hardware landscape without addressing Google's TPU strategy. Google's approach has always been to build custom ASICs optimized for their own workloads, and their latest TPU v5p and the upcoming TPU v7 Ironwood represent significant advances. The Ironwood delivers 4,614 teraflops per second at FP8 precision, with configurations scaling up to 9,100 chips in a single cluster.
What's particularly interesting about Google's TPU approach is how it reflects their broader strategic thinking. By controlling the entire stack, from hardware to software to applications, they can optimize in ways that hardware vendors selling to the broader market cannot. Their latest TPU architectures are specifically tuned for the transformer models that power their search, cloud, and AI products. The TPU v7 includes enhanced sparse core units and improved high-bandwidth memory that's designed specifically for the attention mechanisms that are central to modern language models.
But the broader theme here is that we're seeing the end of one-size-fits-all computing. Just as the smartphone revolution led to ARM processors optimized for mobile workloads, the AI revolution is creating demand for specialized architectures. Training workloads need different optimizations than inference. Real-time applications need different trade-offs than batch processing. Scientific computing needs different capabilities than consumer applications.
And this specialization is creating interesting dynamics in the market. Apple's approach with their M-series chips represents yet another philosophy, bringing AI capabilities directly to the edge with unified memory architectures that excel at on-device inference. Their Apple Intelligence features run locally on iPhones and MacBooks, representing a completely different deployment model than cloud-based AI services.
The Apple approach is particularly smart for privacy-sensitive applications. Instead of sending your data to distant cloud servers for processing, the AI runs right on your device. It's like having a personal AI assistant who never leaves your office, versus one who has to call headquarters for every question. The latency is lower, the privacy is better, but the computational power is necessarily more limited.
Now let's address the elephant in the room: supply and availability. For the past 2 years, AI chip availability has been the primary constraint limiting AI deployment. Organizations that could afford the computational costs still couldn't get access to the hardware they needed. But 2025 has marked a turning point in supply dynamics.
The supply situation in 2025 tells a fascinating story about how quickly industrial capacity can adapt when there's sufficient demand and investment. TSMC, which manufactures chips for most of these companies, allocated 28% of their total wafer capacity to AI chip production in 2025. Samsung achieved 90% yield rates on their 3-nanometer processes specifically for AI applications. The global average lead time for AI chips dropped from over 20 weeks to just 12 weeks.
But the supply improvement isn't just about raw manufacturing capacity, it's about the entire ecosystem maturing. The shortage of specialized substrates that plagued 2023 and 2024 was largely resolved by Q2 2025 through expanded capacity in Taiwan and Malaysia. ASML delivered 57 EUV lithography tools in 2025, enabling more foundries to produce chips at the advanced nodes these AI processors require.
What's really interesting is how this supply improvement is changing the strategic calculations for AI deployment. When chips were scarce, organizations had to make long-term commitments and accept whatever configurations were available. Now, with better availability, we're seeing more sophisticated procurement strategies. Companies are mixing cloud and on-premise deployments, negotiating better pricing through competition between vendors, and right-sizing their infrastructure to specific workloads.
The pricing dynamics are particularly noteworthy. Cloud GPU prices have dropped significantly throughout 2025. H100 instances that cost over $8 per hour in early 2024 are now available for under $3 per hour from competitive providers. This isn't just about supply and demand, it's about the cloud providers themselves building more efficient data centers and achieving better utilization rates.
And this brings us to one of the most important strategic questions facing organizations today, the choice between cloud and on-premise deployment. The improving supply situation has made on-premise deployment viable for more organizations, while competitive cloud pricing has made certain workloads more economical to outsource. The decision increasingly comes down to specific requirements around data sovereignty, control, and utilization patterns.
For training large models from scratch, cloud deployment often makes sense because of the massive computational requirements and the intermittent nature of training runs. But for inference workloads, especially those with consistent demand patterns, on-premise deployment can provide better economics and performance. The key is understanding your specific workload characteristics and optimizing accordingly.
The networking and storage infrastructure supporting these AI chips has become equally important. Modern AI workloads require high-speed interconnects. We're seeing 400 gigabit Ethernet and InfiniBand becoming standard, with specialized AI-optimized storage systems from companies like Pure Storage and Vast Data. The chip is just one component in a complex system that must be optimized holistically.
Looking ahead, several trends are reshaping the landscape. The move towards smaller, more efficient models is creating demand for inference-optimized chips like Grok's LPUs. The growth of edge AI is driving development of specialized processors for mobile and IoT applications. And the emergence of multimodal AI is creating demand for chips that can efficiently handle text, image, video, and audio processing simultaneously.
We're also seeing interesting developments in sustainability and power efficiency. The computational demands of AI are enormous, and data centers are becoming significant consumers of electrical power. New chip architectures are increasingly optimized for performance per watt, not just raw performance. This is driving innovations in chip design, cooling systems, and data center architecture that will have implications far beyond AI.
The implications for organizations are profound. Hardware choices made today will influence AI capabilities for years to come. The performance characteristics of different chip architectures affect which types of AI applications are economically viable. The availability and pricing of different hardware options influence deployment strategies and competitive positioning.
What's particularly exciting is that we're still in the early stages of this hardware evolution. The chips being deployed in 2025 are remarkable, but they're likely to seem primitive compared to what we'll see in 2027 or 2030. The physics of silicon scaling may be approaching limits, but the architectural innovations we're seeing suggest that performance improvements will continue through better design rather than smaller transistors.
And this hardware foundation directly connects to our next episode, where we'll explore the economics of frontier AI labs. The companies developing the most advanced AI models, OpenAI, Anthropic, Google DeepMind, and others, are making massive bets on specific hardware architectures. Their choice of chips, their access to computational resources, and their ability to scale training and inference workloads directly influences their competitive positioning and business models.
The hardware landscape we've discussed today sets the stage for understanding how these frontier labs defend their enormous valuations, how they differentiate their offerings, and why access to compute has become as strategically important as access to data or talent. The chips we've explored aren't just components, they're the foundation that makes the entire AI economy possible.
That brings us to the end of today's deep dive into the compute and hardware landscape powering AI in 2025. From NVIDIA's architectural dominance to the specialized innovations of companies like Grok and Cerebras, from supply constraints easing to new deployment strategies emerging, the hardware foundation of AI continues to evolve rapidly.
Next time on State of the AI Industry 2025, we'll examine how the Frontier AI Labs, the companies pushing the boundaries of what's possible with artificial intelligence, justify their massive valuations and defend their positions against both established competitors and open-source alternatives. Until then, keep building the future.
Welcome to State of the AI Industry 2025. I'm Stephen, and we've already covered the physical foundation of AI through our exploration of hardware and compute infrastructure. Today, we're ascending the stack to examine something equally fascinating and perhaps more volatile: the economics driving the most ambitious AI companies on the planet. These are the Frontier Labs: OpenAI, Anthropic, Google DeepMind, xAI, and others, whose valuations have reached stratospheric heights and whose business models are reshaping the entire technology landscape.
And what makes this particularly intriguing is that we're witnessing a unique moment in tech history. These companies are burning through unprecedented amounts of capital while simultaneously commanding some of the highest private valuations we've ever seen. OpenAI alone is valued at around $300 billion, Anthropic at $183 billion, and Elon Musk's xAI reportedly at $200 billion. Yet the path to sustainable profitability remains largely unproven for most of these players.
That's exactly the paradox we need to unpack. Last episode, we discussed how the hardware layer, those GPUs and TPUs from NVIDIA, AMD, and specialized chip makers, creates the foundation for AI capabilities. But the companies building on that foundation are operating under completely different economic assumptions than traditional software businesses. They're not just building applications, they're essentially racing to capture what could be the next platform shift in computing itself.
Which brings us to today's focus: understanding the revenue models, burn rates, and competitive positioning of these frontier labs. We'll examine how OpenAI generates an estimated $12 billion in revenue while still operating at massive losses, why Anthropic raised $13 billion in just their latest funding round, and what xAI's aggressive federal contracting strategy tells us about the broader market dynamics.
We'll also explore the fundamental question that's keeping investors and industry observers awake at night. Can these astronomical valuations be justified? Are we witnessing the birth of the next generation of platform companies, or are we in the midst of an unsustainable capital allocation bubble?
The stakes couldn't be higher. These aren't just software companies. They're positioning themselves to become the infrastructure layer for artificial intelligence itself. And unlike previous technology waves where network effects and data advantages created defensible moats, the AI landscape presents unique challenges to maintaining competitive positioning.
Let's start with the current state of the market. When we look at the funding landscape for AI companies in 2025, we're seeing numbers that would have seemed impossible just a few years ago. According to recent data, AI companies account for 58 cents of every venture capital dollar deployed this year. That's not just a significant portion, that's an overwhelming majority of all venture investment flowing into a single technology category.
And the burn rates reflect this capital intensity. The median Series A AI company burns $5 to generate $1 of new revenue. Compare that to traditional SaaS companies, where venture capitalists typically prefer burn multiples below 2 times. AI companies are operating under fundamentally different unit economics, largely because of their massive infrastructure requirements and the competitive dynamics forcing rapid scaling.
Let's break down the revenue models that these labs are pursuing. OpenAI has become the template here, with multiple revenue streams: API usage, enterprise subscriptions through ChatGPT, licensing deals like their partnership with Microsoft, and consumer subscriptions. But what's fascinating is how quickly these models are evolving.
OpenAI's numbers are particularly revealing. They generated approximately $4.3 billion in revenue in the first half of 2025, putting them on track for their projected $12 to $13 billion annual target. But they're also burning cash at an extraordinary rate, about $2.5 billion in the first half of the year, primarily on research and development costs.
This creates an interesting dynamic. OpenAI is scaling revenue faster than almost any enterprise software company in history. They've gone from essentially zero revenue to projected $12 billion in just a few years. But they're also spending at a pace that would be unsustainable for most businesses. The question becomes, are they building a moat that justifies this level of investment?
Anthropic presents a fascinating counterpoint. Their $13 billion Series F round at a $183 billion valuation reflects different strategic priorities. While OpenAI has focused heavily on consumer adoption and broad API distribution, Anthropic has positioned itself more explicitly around safety, compliance, and enterprise trust. Their Claude Code product alone is generating over $500 million in run rate revenue.
The competition dynamics here are unlike anything we've seen in previous technology cycles. In traditional software, companies could differentiate through features, user experience, or vertical specialization. But in AI, the models themselves are converging towards similar capabilities, which means differentiation increasingly comes down to factors like safety, reliability, cost, and ecosystem integration.
This is where Google DeepMind's strategy becomes particularly interesting. Unlike the pure-play AI companies, Google can afford to treat Gemini as a strategic investment rather than a standalone profit center. They're integrating AI capabilities across their entire ecosystem: search, ads, workspace, cloud, which means they can subsidize model development costs against existing revenue streams.
That asymmetry creates significant competitive pressure on independent labs. When Google can essentially give away AI capabilities as part of their broader platform strategy, it forces companies like OpenAI and Anthropic to prove exceptional value in order to command premium pricing.
And then there's xAI, which represents yet another approach. Elon Musk's company has raised $10 billion at a $200 billion valuation, but their strategy seems focused on integration with the broader Musk ecosystem: X for data, Tesla for robotics applications, and aggressive pricing for enterprise contracts. They're reportedly offering federal government services at just 42 cents per dollar of standard pricing.
That pricing strategy reveals something crucial about the current market dynamics. These companies aren't just competing on technology, they're competing on their ability to sustain losses while building market share. It's a classic market penetration strategy, but applied at a scale that's unprecedented in enterprise software.
Which brings us to the sustainability question. The numbers are staggering when you look at the collective capital requirements. OpenAI has raised over $40 billion with commitments. Anthropic has raised over $20 billion, including their latest round. xAI has raised over $20 billion, and that's just the top 3 players. We're talking about over $80 billion in capital deployed into frontier AI development.
And that doesn't include the capital investments from incumbents. Google is spending tens of billions on AI research and infrastructure. Microsoft has committed to similar levels of investment, and even companies like Meta are allocating enormous resources to AI development. The total industry investment is approaching levels that would fund entire sectors of the economy.
From an economic perspective, this level of capital allocation only makes sense if the addressable market is truly enormous. The bulls make the case that AI will automate or enhance virtually every knowledge work function, representing trillions of dollars in economic value. But that transformation depends on these models actually delivering productivity gains that justify their costs.
The revenue concentration is another fascinating aspect. Despite all this investment and competition, revenue appears to be concentrating among a small number of players. OpenAI still appears to command the largest market share in terms of API usage and consumer adoption, though the gaps are narrowing as competitors improve their models and pricing.
But here's where the economics get really interesting: the marginal cost structure of AI inference. Unlike traditional software, where additional users typically have near zero marginal costs, AI models require compute resources for every interaction. This means that even successful AI companies face ongoing variable costs that scale with usage.
That creates a fundamentally different economic dynamic. In traditional SaaS, once you've acquired a customer, additional usage is essentially pure profit. But in AI services, higher usage means higher infrastructure costs, which puts pressure on unit economics in ways that traditional software companies haven't had to manage.
The infrastructure costs are particularly brutal for frontier models. Training a state-of-the-art language model can cost tens or hundreds of millions of dollars, and that's before considering the ongoing inference costs. Companies like OpenAI are reportedly spending billions annually just on compute resources from providers like Microsoft Azure.
This is where the hardware discussion from our previous episode becomes critical. The companies that can secure access to the latest GPUs and optimize their inference infrastructure have significant cost advantages. It's creating a new form of vertical integration, where AI companies are thinking about everything from chip design to data center operations.
The venture capital dynamics reflect this reality. Unlike traditional software investments, where a few $1,000,000 might fund a company to profitability, AI companies are raising hundreds of millions or billions of dollars in single rounds. The capital intensity is pushing venture economics toward a model that looks more like infrastructure or biotech investing.
And the timeline to profitability is extending accordingly. Traditional SaaS companies might reach cash flow positive within 3 to 5 years of founding. But frontier AI companies are operating on longer timelines, with the assumption that they need to capture significant market share before focusing on profitability.
The competitive moats in this space are still being defined. Traditional software companies could build defensibility through network effects, switching costs, or proprietary data. But AI models can be retrained, APIs can be replaced, and capabilities are becoming increasingly commoditized across providers.
Which suggests that the long-term winners will be determined by factors beyond just model performance. Companies that can build sustainable cost advantages, create ecosystem lock-in, or capture proprietary data sources will likely maintain competitive positioning as the technology matures.
The regulatory environment adds another layer of complexity. As these companies scale, they're facing increasing scrutiny around safety, bias, privacy, and market concentration. The compliance costs and regulatory constraints could significantly impact their economic models, particularly for companies operating in regulated industries.
Looking at the international dimension, it's striking how concentrated the funding and development is in the U.S. market. American companies have raised over $100 billion in AI investment in 2024 alone, compared to less than $10 billion in China and $4.5 billion in the UK. That concentration creates both opportunities and vulnerabilities.
The talent costs are another significant factor. These companies are competing for a limited pool of AI researchers and engineers, driving compensation to extraordinary levels. It's not uncommon for senior AI researchers to command compensation packages worth millions of dollars annually.
That talent concentration is creating its own economic dynamics. Companies are essentially bidding against each other for human capital, which drives up operating costs across the entire sector. And unlike traditional software, where developer productivity tools can create significant leverage, AI research still requires highly specialized human expertise.
The customer concentration patterns are also revealing. While these companies talk about democratizing AI access, the reality is that a significant portion of their revenue comes from large enterprise customers and cloud partnerships. OpenAI's Microsoft relationship, Anthropic's enterprise focus, and Google's internal integration all reflect the importance of high-value customer relationships.
As we look toward the sustainability of these economic models, several factors will determine which companies can transition from growth at all costs to sustainable profitability. Cost optimization, pricing power, customer retention, and the ability to expand beyond pure AI services into broader platform businesses will all be critical.
The timeline for this transition is accelerating. While these companies might have expected longer runway to prove their models, the capital markets are increasingly focused on paths to profitability. The companies that can demonstrate improving unit economics and expanding gross margins will likely have continued access to capital, while those that can't may face significant pressure.
Which brings us to the broader implications for the technology ecosystem. If these companies succeed in building sustainable businesses at their current valuations, they'll represent some of the largest and most valuable technology companies ever created. But if the economics don't work out, the capital destruction could be unprecedented.
The opportunity cost considerations are significant as well. All this capital being deployed into AI development represents resources that could be invested in other areas of innovation. The success or failure of these economic bets will have implications far beyond just the AI sector.
Looking ahead, we're likely to see continued consolidation as companies either achieve sustainable economics or run out of funding. The companies with the strongest fundamentals, best cost structures, and most defensible market positions will likely acquire or outlast their competitors.
And the successful companies will probably look quite different from what we see today. Rather than pure-play AI model providers, the winners will likely be companies that have integrated AI capabilities into broader platform businesses, creating multiple revenue streams and sustainable competitive advantages.
Which suggests that the economics of frontier AI labs represent one of the most fascinating and high-stakes experiments in technology history. These companies are attempting to build businesses around capabilities that didn't exist just a few years ago, using economic models that are still being defined, in a market where the ultimate size and structure remain highly uncertain.
What's certain is that the current funding levels and burn rates are unsustainable indefinitely. Over the next few years, we'll see which companies can transition to sustainable economics and which cannot. The answers will shape not just the AI industry, but potentially the entire technology landscape for decades to come.
Next week, we'll examine how open-source AI models are disrupting this entire economic equation. While frontier labs are raising billions to develop proprietary models, companies like Meta are releasing increasingly capable open-source alternatives that challenge the fundamental assumptions about AI economics and competitive positioning. Join us as we explore the open-source ecosystem and what it means for the future of AI development. Welcome to State of the AI Industry 2025. I'm Stephen, and I'm joined by my co-host Edith. Today, we're diving deep into what might be the most democratic force in artificial intelligence right now, the open-source ecosystem. Last episode, we explored the billion-dollar economics of frontier labs like OpenAI and Anthropic. But there's another side to this story that's equally compelling and potentially even more transformative for the industry.
Absolutely, Stephen. We're witnessing a fascinating paradox in AI right now. While these frontier labs are commanding astronomical valuations, there's simultaneously an explosion of incredibly capable open-source models that anyone can download, modify, and deploy. Today, we'll examine the leading open-source models across text, vision, audio, and code generation, explore the various licensing approaches that govern their use, and analyze the complex economics of adopting open-source AI in enterprise environments.
What makes this topic particularly intriguing is how it connects to everything we've discussed previously. The same hardware infrastructure we covered in earlier episodes powers both proprietary and open-source deployments. The economic pressures we just analyzed in frontier labs are directly driving some organizations to explore open-source alternatives. And as we'll see in our next episode on agentic AI, many of the most innovative agent frameworks are being built on top of these open-source foundations.
Let's start with the current landscape of top-performing open-source models, because the quality gap between open and closed models has narrowed dramatically. In the text domain, we have Meta's Llama 3 with its massive 405 billion parameter variant, released under a permissive CC BY license. This model represents a watershed moment because it's the first open-source model that genuinely rivals GPT-4 level performance on many benchmarks.
The significance of Llama 3 405B cannot be overstated. When Meta released this model, they essentially open-sourced capabilities that would have cost millions of dollars to develop and required the computational resources typically reserved for the largest tech companies. The model achieves competitive performance on benchmarks like MMLU, where it scores comparably to proprietary models that cost significant money to access via API.
Think of it like this. Imagine if Tesla suddenly open-sourced all their autonomous driving technology, complete blueprints, and manufacturing processes. That's essentially what Meta did with Llama 3. They took capabilities that were previously locked behind API paywalls and made them freely available for anyone to download and customize. The smaller variants, Llama 2 70B with Apache 2 licensing, provide a more computationally accessible entry point while still delivering impressive performance.
Moving beyond Meta's offerings, we see Mistral's contributions with their Magistral Small and the popular Mixtral models. Mistral's Mixtral 7B and 34B use a mixture of experts architecture that's particularly interesting from a computational efficiency standpoint. The 8x7B variant achieves performance comparable to much larger traditional models while using only a fraction of the active parameters during inference.
The architectural innovation here is fascinating. Imagine having a team of 8 specialists, but for any given problem, you only consult the 2 most relevant experts. That's essentially how Mixture of Experts works. Mixtral activates only about 12 to 13 billion parameters per token while maintaining the knowledge capacity of a much larger model. This makes it incredibly cost-effective for deployment, especially when you're managing inference costs across thousands or millions of requests.
The benchmarking data supports this efficiency claim. On coding benchmarks, Mixtral 8x7B outperforms Llama 270B while requiring significantly less computational resources. This performance per dollar ratio is crucial for organizations evaluating their total cost of ownership. A smaller organization can run Mixtral on consumer-grade hardware that would struggle with the larger Llama models.
Beyond text models, the open-source ecosystem has produced remarkable capabilities in specialized domains. For vision tasks, Stable Diffusion remains the flagship open-source text-to-image model. Unlike proprietary alternatives like DALL-E or Midjourney, Stable Diffusion can be run locally, fine-tuned on custom datasets, and integrated into enterprise workflows without sending data to external services.
Stable Diffusion's impact extends far beyond individual creators generating artwork. Enterprises are using it for rapid prototyping and product design, generating diverse training data for other AI models, and creating customized visual content at scale. The ability to fine-tune the model means companies can adapt it to their specific brand aesthetics or technical requirements in ways that simply aren't possible with API-based services.
For computer vision tasks beyond generation, we have the Segment Anything model from Meta. SAM represents a breakthrough in promptable segmentation. You can click on any object in any image, and it will accurately segment it out. This might sound simple, but the technical achievement is remarkable. Traditional segmentation models required specific training for each type of object. SAM works on virtually anything without task-specific training.
SAM's zero-shot capabilities are particularly valuable for enterprises dealing with diverse visual content. A retail company could use it to automatically segment products and catalog photos. A medical research organization could isolate anatomical structures in imaging data. And a manufacturing company could identify components in inspection imagery. The model's 1.1 billion mask training dataset enables this level of generalization.
In the audio domain, models like VoiceBox demonstrate sophisticated capabilities for speech generation and manipulation. VoiceBox can synthesize speech in 6 languages, remove background noise from recordings, and even edit speech content by regenerating specific portions. It represents the kind of multimodal, multilingual capability that was previously exclusive to large tech companies.
The code generation space has seen particularly rapid advancement with models like StarCoder. The 55 billion parameter version demonstrates state-of-the-art performance on programming benchmarks, often matching or exceeding proprietary alternatives like GitHub Copilot's underlying models. StarCoder supports over 80 programming languages and includes advanced capabilities like fill-in-the-middle code completion.
What's especially important about StarCoder is its training methodology. Unlike some proprietary models that may have unclear data provenance, StarCoder is trained on the stack, a carefully curated dataset of permissively licensed code. This transparency addresses some of the copyright concerns that enterprises have when adopting AI-generated code, though legal questions certainly remain complex.
This brings us to one of the most critical aspects of the open-source AI ecosystem, licensing. The landscape here is surprisingly complex, with different models using different licensing approaches that have significant implications for commercial use. Understanding these licenses is absolutely essential for any organization considering open-source AI adoption.
License selection in open-source AI is like choosing the rules of engagement for your AI deployment. At one end of the spectrum, we have highly permissive licenses like MIT and Apache 2. The MIT license is about as open as you can get. You can use the software for any purpose, modify it, distribute it, even incorporate it into proprietary products. The only requirement is that you include the original copyright notice.
Apache 2.0 adds some additional protections, particularly around patent rights. It includes explicit patent grants from contributors, which provides some legal safety for users. This makes Apache 2.0 particularly attractive for enterprise environments where patent litigation risks are a concern. Many of the Mistral models use Apache 2.0 licensing, which partly explains their popularity in commercial settings.
Creative Commons licenses add another layer of complexity. CC BY, used by some Llama models, allows virtually unrestricted use as long as you provide attribution. But enterprises need to be careful about other Creative Commons variants. CC BY NC restricts commercial use, CC BY SA requires derivative works to use the same license, and CC BY ND prohibits modifications entirely.
The licensing landscape becomes even more nuanced when you consider that AI models often have multiple license layers. The model weights might be under one license, the training code under another, and any associated datasets under yet another license. Enterprises need to analyze all these components to understand their obligations and restrictions.
Some model creators are introducing custom licenses tailored specifically for AI applications. Stability AI, for instance, has created tiered licensing for newer Stable Diffusion models. Their community license allows free commercial use for organizations below a certain revenue threshold, while larger enterprises need to purchase a commercial license. This approach tries to balance open access with sustainable business models.
These licensing considerations directly impact the economic analysis of open-source adoption. While the models themselves may be freely available, deploying them effectively requires significant infrastructure and expertise investments. This is where the total cost of ownership calculation becomes crucial for enterprise decision-making.
Think of open-source AI like buying a high-performance sports car that comes without an engine, transmission, or electronics, but you get the complete blueprints. Yes, the chassis is free, but building a functional vehicle requires substantial additional investment. With open-source AI, you get the model weights for free, but you need infrastructure, engineering expertise, and ongoing operational support to make them production-ready.
The infrastructure costs alone can be substantial. Running Llama 3 405B requires multiple high-end GPUs with significant VRAM. A typical deployment might need 8 H100 GPUs, which could cost hundreds of thousands of dollars in hardware or thousands of dollars per month in cloud computing fees. Smaller models like Mistral 8x7B are more accessible, potentially running on single consumer-grade GPUs, but still require careful resource planning.
Beyond hardware, there are significant human capital requirements. Organizations need AI engineers who can optimize models for their specific use cases, DevOps professionals who can manage the deployment infrastructure, and ongoing support staff to monitor performance and handle issues. These expertise requirements can easily cost more annually than API fees for equivalent proprietary services, especially for smaller deployments.
However, the economics can shift dramatically at scale. Organizations processing millions of requests per month may find that the fixed costs of open-source deployment become more attractive than the variable costs of API-based services. There's also the value of control and customization that's difficult to quantify but potentially very valuable for certain use cases.
This creates three primary adoption archetypes we see in the market. First is self-hosted deployment, where organizations run models on their own infrastructure. This provides maximum control and data privacy, but requires the highest upfront investment and ongoing operational expertise.
The second archetype is managed cloud deployment, where cloud providers offer hosted versions of open-source models. Services like Amazon Bedrock, Azure AI, or Google Vertex AI provide open-source models with the convenience of managed infrastructure. This reduces operational burden while maintaining some of the flexibility benefits of open-source models.
The third approach is hybrid deployment, where organizations use a mix of open source and proprietary models depending on the specific use case. They might use open source models for internal tooling or development work where data sensitivity is lower, while relying on proprietary APIs for customer-facing applications where reliability and support are paramount.
This hybrid approach often makes the most sense from a risk management perspective. Organizations can experiment with open-source models, build internal expertise, and gradually expand their usage as they become more comfortable with the technology. It also provides leverage in negotiations with proprietary AI providers. Having viable alternatives improves your bargaining position.
The governance and risk considerations for open-source AI are particularly complex. Unlike proprietary services that come with service-level agreements and support guarantees, open-source models require organizations to take full responsibility for their behavior and performance. This includes implementing appropriate safety guardrails, monitoring for bias or harmful outputs, and ensuring compliance with relevant regulations.
Interestingly, some organizations find that the transparency of open-source models actually helps with governance and compliance. They can audit the training data, understand the model architecture, and implement custom safety measures that aren't possible with black-box proprietary services. However, this transparency comes with the responsibility to actually perform that governance work.
The intellectual property landscape around open-source AI remains murky and rapidly evolving. While the model licenses may be clear, questions about training data provenance, potential copyright infringement in generated outputs, and liability for AI-generated content are still being worked out in courts and regulatory bodies. Organizations need to factor this uncertainty into their risk assessments.
Looking at current adoption patterns, we see strong uptake in certain sectors and use cases. Technology companies, particularly those with existing open-source expertise, are leading adoption. Research institutions appreciate the ability to modify and extend models for their specific needs. Startups often choose open-source models to minimize initial costs and avoid vendor lock-in.
The adoption is also geography-dependent, with organizations in regions that have data sovereignty requirements or limited access to US-based AI services showing strong interest in locally deployable open-source alternatives. The ability to keep data processing entirely within national boundaries is increasingly valuable from both regulatory and strategic perspectives.
The third approach is performance-wise. The gap between open-source and proprietary models continues to narrow. In many benchmarks, the best open-source models now match or exceed the performance of proprietary alternatives from just a year ago. While frontier models like GPT-4o or Claude Sonnet may maintain some performance advantages, the rate of improvement in open-source alternatives suggests this gap may not persist.
What's particularly exciting is how open-source models are accelerating innovation in the broader AI ecosystem. Because researchers and developers can access and modify these models, we're seeing rapid development of new techniques, architectures, and applications that build on these foundations. This creates a virtuous cycle where open research accelerates the development of even better models.
The economic implications extend beyond individual organizations to the broader AI market structure. Wide availability of capable open-source models puts competitive pressure on proprietary AI providers. They need to justify their pricing through superior performance, better user experience, or additional services that go beyond raw model capabilities.
This competitive dynamic is healthy for the market overall. It prevents excessive concentration of AI capabilities in a few large companies and creates opportunities for innovation at every level of the stack. Smaller organizations can build competitive AI applications without needing to develop foundational models from scratch, while larger organizations have alternatives that reduce their dependence on any single AI provider.
For organizations evaluating open-source AI adoption, the key is to think strategically about their specific requirements, constraints, and capabilities. The choice between open-source and proprietary solutions isn't binary. Most successful AI strategies will likely involve elements of both approaches optimized for different use cases and requirements.
The most successful open-source AI adoptions we see tend to start small and scale gradually. Organizations begin with pilot projects in low-risk areas, build internal expertise and infrastructure, and then expand usage as they become more comfortable with the technology. This approach allows them to realize benefits while managing risks and building organizational capabilities.
As we wrap up today's discussion, it's worth noting how this open-source foundation enables many of the advanced applications we'll be exploring next. The agentic AI systems and model context protocol implementations we'll discuss in our next episode rely heavily on the open-source models and tools we've covered today. These models provide the accessible, customizable foundation that makes sophisticated AI agents possible for a much broader range of organizations.
The open-source AI ecosystem represents both a technical achievement and a philosophical approach to AI development. It embodies the idea that transformative AI capabilities should be widely accessible rather than concentrated in a few large organizations. While challenges around economics, governance, and risk management remain significant, the continued advancement and adoption of open-source AI models suggests this approach will play an increasingly important role in shaping the future of artificial intelligence.
Next time on State of the AI Industry 2025, we'll explore how these open-source foundations enable the next major wave of AI innovation, autonomous agents, and the emerging model context protocol that's creating new standards for how AI systems interact with data and tools. Until then, thank you for joining us.
Thank you for listening, and we'll see you next time.
Welcome to State of the AI Industry 2025. I'm Steven, and today we're stepping into one of the most transformative layers of the AI ecosystem, the world of agentic AI and the revolutionary Model Context Protocol. In our last episode, we explored the open source landscape, where we witnessed the democratization of powerful models and the intricate balance between permissive and restrictive licensing. But now we face a fundamental shift in how AI systems operate. They're no longer just responding to queries. They're planning, reasoning, executing multi-step workflows, and connecting to real-world systems in ways we've never seen before.
That's right, and this evolution represents something truly unprecedented. We're moving from AI that simply generates text or code to AI that acts as an autonomous digital workforce. Today, we'll unpack the technical architecture behind agentic AI, explore how the Model Context Protocol is becoming the universal language for AI-to-system communication, and examine the frameworks that are making this possible, from LangChain and AutoGPT to Microsoft's prompt flow. We'll also dive into the critical governance challenges that emerge when AI systems start making decisions and taking actions on their own.
Before we begin, let's establish what we're really talking about here. When we say agentic AI, we're not just describing chatbots with better responses. These are AI systems that can autonomously plan sequences of actions, maintain state across complex workflows, operate with external tools and APIs, and execute multi-step processes with minimal human intervention. The key distinction is autonomy. These systems can take a high-level goal and break it down into actionable steps, then execute those steps while adapting to changing conditions.
Think of it like the difference between having a research assistant who can answer questions versus one who can independently conduct an entire research project. The first assistant waits for your specific questions and provides answers. The second assistant takes your research objective, develops a methodology, gathers data from multiple sources, analyzes findings, and delivers a comprehensive report, all while keeping you updated on progress and asking for clarification only when truly necessary.
That analogy perfectly captures the paradigm shift we're witnessing. But this transformation isn't happening in isolation. It's being enabled by a critical piece of infrastructure called the Model Context Protocol, or MCP. Introduced by Anthropic in late 2024, MCP is solving what we call the N by M integration problem, where every AI application previously needed custom connectors for every external system it wanted to access.
MCP is essentially creating a universal language for AI systems to communicate with external tools and data sources. Instead of building separate integrations for each combination of AI application and external system, MCP provides a standardized JSON RPC protocol that allows any MCP-compliant AI system to work with any MCP-compliant server. It's like having a universal adapter that works across all your devices. Except in this case, it's allowing AI agents to seamlessly connect to databases, APIs, file systems, and enterprise applications.
The technical architecture of MCP is elegantly simple yet powerful. It follows a client-server model with three core components: MCP hosts, which are the AI-powered applications like Claude Desktop or AI-enhanced IDEs, MCP clients, which are embedded within these host applications and manage connections to external systems, and MCP servers, which expose specific capabilities like database access or API integrations. The communication happens over standard transport protocols, STDI for local integrations, and HTTP with server-sent events for remote connections.
What makes MCP particularly compelling is how it addresses the context problem that has plagued AI systems. Traditional AI models are limited to their training data and whatever context you provide in a single conversation. With MCP, agents can dynamically fetch real-time information, execute functions, and maintain persistent connections to live data sources. This means an AI agent can check your calendar, query your database, send emails, and update project management systems all within a single workflow.
The early adoption of MCP has been remarkably swift. Companies like Block and Apollo integrated MCP into their systems immediately after its release. Development tool companies including Zed, Replit, Codium, and Sourcegraph are building MCP support to enhance their AI coding assistants. What's particularly interesting is how this protocol is enabling a new generation of use cases that were previously impossible or required extensive custom development.
Let's examine some concrete applications. In IT service automation, an MCP-enabled agent can receive a support ticket, analyze the issue, check system logs through one MCP server, query the knowledge base through another, and automatically resolve common problems or escalate complex issues with full context. For customer support, agents can access CRM data, check order histories, process refunds, and update customer records, all while maintaining a natural conversation with the customer.
The coding assistant use case is particularly sophisticated. An MCP-enabled AI can access your code repository, understand the project structure, check CI/CD pipeline status, run tests, and even deploy code. This goes far beyond code completion. It's about understanding the entire development lifecycle and providing assistance at each stage. Similarly, in legal contract analysis, agents can retrieve relevant case law, check regulatory compliance databases, and draft contract modifications based on current legal standards.
But MCP is just one piece of the agentic AI puzzle. The frameworks that orchestrate these capabilities are equally important. LangChain has evolved from a simple prompt management tool into a comprehensive platform for building complex, multi-agent systems. Its modular architecture allows developers to chain together different AI capabilities, manage context across conversations, and integrate with hundreds of external APIs and tools.
AutoGPT represents a different philosophy, fully autonomous operation with minimal human intervention. Unlike LangChain's structured approach, AutoGPT allows AI agents to set their own goals, plan their own workflows, and execute tasks independently. This autonomous cycle involves receiving a high-level objective, decomposing it into subtasks, gathering information, executing code, and iteratively refining the approach based on results.
Microsoft's Prompt Flow brings enterprise-grade orchestration to the mix. It provides visual workflow design tools, robust integration capabilities, and production-ready deployment options. Prompt Flow excels at creating deterministic, auditable AI workflows, something crucial for enterprise applications where you need to understand exactly how decisions are being made and ensure consistent outcomes.
Llama Index, originally focused on retrieval-augmented generation, has evolved to include sophisticated agent capabilities. It excels at scenarios where you need to query and synthesize information from large document collections, making it particularly valuable for knowledge management and research applications.
The real power emerges when these frameworks work together. You might use Llama Index for data retrieval, LangChain for workflow orchestration, and MCP for system integration, creating a comprehensive agentic AI stack that can handle complex, multi-step business processes.
However, with this power comes significant responsibility. Agent AI systems introduce governance challenges that don't exist with traditional software. When an AI system can independently make decisions and take actions, organizations need robust frameworks for monitoring, control, and accountability.
The governance approach needs to be comprehensive yet practical. Organizations are starting with sandbox deployment environments where agents can operate safely without affecting production systems. They're implementing graduated autonomy controls, starting with highly supervised agents and gradually increasing independence as the systems prove reliable. Human-in-the-loop mechanisms ensure that critical decisions still require human approval.
Risk-based deployment is becoming the standard approach. Low-stakes use cases like data analysis and report generation are perfect starting points. As organizations build confidence and refine their governance processes, they can expand to higher-impact applications like customer service automation and financial processing.
Monitoring and evaluation present unique challenges because traditional software testing methods don't fully capture agentic behavior. Red teaming efforts are emerging specifically for autonomous AI systems, focusing on scenarios like plan deviation, tool misuse, and unintended consequences. The Cloud Security Alliance recently released a comprehensive red teaming guide specifically for agentic AI systems, highlighting 12 high-risk threat categories, including orchestration logic attacks and autonomous decision loop manipulation.
Custom evaluation frameworks are becoming essential. Organizations need to assess not just whether an agent produces correct outputs, but whether it follows appropriate decision-making processes, uses tools responsibly, and maintains transparency in its reasoning. The benchmarks used for traditional AI models simply don't capture the complexity of autonomous behavior.
Transparency and explainability are particularly critical. When an AI agent makes a decision that affects business operations or customer interactions, stakeholders need to understand not just what decision was made, but why it was made and what information was considered. This requires comprehensive logging of decision chains, tool usage patterns, and data access activities.
The security implications are profound. Agent AI systems need unique digital identities with carefully managed permissions. Zero-trust architectures become essential because agents can act unpredictably and access multiple systems. Identity-based access control, continuous monitoring, and dynamic permission adjustment are becoming fundamental requirements.
Let's talk about the current state of the ecosystem. The rapid development pace is remarkable. New frameworks, tools, and capabilities are emerging monthly. However, the field is still maturing. Many organizations are in the experimentation phase, running pilots and building internal expertise before committing to production deployments.
The integration complexity shouldn't be underestimated. While MCP promises standardized connectivity, organizations still need to invest in API exposure, security hardening, and system integration. The enterprise readiness gap is significant. Many companies aren't prepared for the infrastructure changes required to support agent AI effectively.
Performance and reliability remain ongoing challenges. Agentic systems are inherently more complex than single-model applications, with more potential failure points. Latency can accumulate across multiple tool calls and API interactions. Error handling and recovery mechanisms need to be sophisticated enough to deal with partial failures and unexpected responses from external systems.
The talent requirements are evolving rapidly. Organizations need people who understand not just AI and machine learning, but also system architecture, security, governance, and the specific business domains where agents will operate. The interdisciplinary nature of agentic AI development is creating new career paths and skill requirements. Looking ahead, we're seeing rapid convergence around standards and best practices. Multi-agent platforms are becoming more sophisticated, enabling complex workflows where specialized agents collaborate on larger tasks. The standardization around protocols like MCP is accelerating interoperability and reducing development overhead.
Policy frameworks are also evolving. Governments and regulatory bodies are beginning to address autonomous AI systems specifically, recognizing that traditional software regulations don't fully capture the risks and requirements of systems that can make independent decisions.
The economic implications are substantial. Agentic AI promises to automate not just routine tasks, but entire workflows and processes. This could fundamentally change how organizations operate, potentially reducing costs and increasing efficiency while requiring significant investment in new infrastructure and capabilities.
What's particularly exciting is the emergence of agentic-only vulnerabilities and capabilities. Researchers are discovering that some attack vectors only work against agents operating in full autonomous mode, while certain beneficial behaviors only emerge when AI systems have the freedom to plan and execute complex workflows.
The key insight for organizations is that agentic AI represents a fundamental architectural shift, not just an incremental improvement.
Success requires rethinking not just how AI fits into existing processes, but how processes themselves should be redesigned for an agentic world.
As we wrap up our exploration of agentic AI and MCP, it's clear we're witnessing the foundation being laid for a new computing paradigm. AI systems are evolving from tools that assist with specific tasks to autonomous agents that can manage entire workflows and business processes.
The convergence of powerful language models, standardized integration protocols, and sophisticated orchestration frameworks is creating possibilities that were pure science fiction just a few years ago. But with these capabilities come new responsibilities for governance, security, and ethical deployment. In our next episode, we'll explore how this agentic AI revolution is creating entirely new markets and business opportunities. We'll dive into the second-order effects of generative AI, examining how it's enabling new content creation pipelines, synthetic data generation, AI operations marketplaces, and rights management technologies. These ecosystem effects represent the next wave of innovation built on the foundation we've discussed today.
From watermarked content and blockchain-based rights registries to specialized data labeling services and model routing systems, the agentic AI revolution is spawning an entire economy of supporting services and technologies. Join us as we map out this expanding ecosystem and its implications for businesses and developers.
Until then, remember that we're not just witnessing the evolution of AI, we're participating in the creation of a new digital infrastructure that will shape how business, creativity, and human AI collaboration unfold in the years ahead. Thanks for joining us on State of the AI Industry 2025.
Welcome to State of the AI Industry 2025. I'm Steven, and today we're diving into something that's become absolutely fundamental to understanding where AI is headed, the second-order markets that generative AI has enabled. When most people think about AI, they focus on the big models, the training infrastructure, the chips. But what we're witnessing now is the emergence of entirely new economic ecosystems built around AI's capabilities.
That's exactly right, Stephen. And what makes this particularly fascinating is that these aren't just incremental improvements to existing workflows. We're seeing the birth of completely new market categories. Today, we'll explore the content creation pipelines that are revolutionizing everything from video production to 3D environments, the synthetic data markets that are solving privacy and scale challenges, the safety evaluation tools that have become critical infrastructure, and the AI operations marketplaces that are optimizing model deployment.
What's crucial to understand here is how these second-order effects build on the foundational work we discussed in our last episode on agentic AI and the Model Context Protocol. While MCP gives agents standardized access to data sources, these emerging markets are creating the actual content, data, and operational infrastructure that those agents will increasingly rely on. It's a perfect example of how each layer of the AI stack enables and amplifies the others.
Think of it like the internet boom of the late 90s. First came the infrastructure, the cables, servers, and protocols. But the real economic explosion happened when entire new industries emerged on top of that foundation: e-commerce, social media, cloud services. We're seeing the same pattern with AI right now, except it's happening at lightning speed.
Let's start with content creation pipelines, because this is where the transformation is most visible to everyday users. We're talking about tools like Runway's Gen 2 and Gen 3 for video generation, Adobe Firefly for comprehensive creative workflows, Lovo and Papercup for voice and dubbing, and companies like Iva and Soundful for music composition.
The scale of change here is staggering. According to recent data, the generative AI market is expected to reach over $62 billion in 2025, with a compound annual growth rate of 46%. But what's really interesting is how these tools are reshaping the economics of content production. Traditional video production might cost thousands of dollars per minute and take weeks to complete. With AI-powered tools, creators can generate high-quality content in hours for a fraction of the cost.
Adobe's recent expansion of their Firefly ecosystem perfectly illustrates this trend. They've integrated models from partners like Runway, Luma AI, Pika, and Google, giving creators unprecedented choice in aesthetic styles and capabilities. This isn't just about making content faster, it's about democratizing creative capabilities that were previously accessible only to well-funded studios.
Here's a concrete example. Imagine you're a small marketing agency creating a product video. Previously, you'd need to hire videographers, rent equipment, secure locations, coordinate actors, easily a $50,000 production. Now, you can use Runway for video generation, Lovo for professional voiceover, and Soundful for custom music, completing the entire project for under $500 in a single day.
This brings us to our second major category, synthetic data and simulation markets. Companies like Simulacra, Mostly AI, and Synthetics are creating artificial data sets that mirror real-world data while maintaining privacy compliance. The market for synthetic data is projected to grow from $486 million in 2025 to over $3 billion by 2032, with a 30.6% annual growth rate.
The use cases here are particularly compelling. In autonomous vehicle development, companies can generate thousands of driving scenarios that would be dangerous or impossible to capture in real life. Healthcare organizations can create patient-like datasets for AI training without exposing sensitive medical information. Financial institutions can test fraud detection systems using synthetic transaction data.
Gartner predicts that by 2030, synthetic data will constitute more than 95% of data used for training AI models in images and videos. This isn't just about volume, it's about filling critical gaps. Real-world datasets often lack sufficient examples of edge cases or rare events. Synthetic data can generate these scenarios on demand.
But there's a crucial challenge here that we need to address: quality validation. Creating synthetic data that truly represents real-world distributions without avoiding bias is incredibly difficult. Companies like Mostly AI and Hazy are developing sophisticated validation frameworks, but this remains an area where human expertise is essential.
This connects directly to our third category, safety evaluation and rights technology. As AI-generated content becomes ubiquitous, we need robust systems to detect it, evaluate its safety, and protect intellectual property. Tools like Google's SynthID for watermarking, Amazon's Content Moderator, and various explainability platforms have become critical infrastructure.
Google's SynthID is particularly interesting because it embeds invisible watermarks directly into AI-generated content during the creation process. Unlike traditional watermarks that can be removed by cropping or editing, SynthID's patterns survive most modifications. Google has also open-sourced the technology, encouraging industry-wide adoption.
The broader safety evaluation market is evolving rapidly. Stanford's AI risk benchmark evaluates models across 314 granular risk categories, while organizations like Future of Life Institute are developing comprehensive safety indices for AI companies. These aren't academic exercises, they're becoming requirements for enterprise deployment. Copyright and intellectual property protection is another massive challenge. As AI models become more capable, the line between inspiration and infringement becomes increasingly blurred. Blockchain-based registries and automated IP clearance systems are emerging to help creators protect their work while enabling legitimate AI training. Now let's examine AI operations and marketplaces, perhaps the most technically sophisticated of these second-order markets. This includes data labeling companies like Scale AI, prompt optimization platforms like PromptBase, and model routing systems that automatically select the best model for each query. Scale AI has become particularly dominant in the data labeling space, working with major companies in autonomous driving, defense, and healthcare. They've evolved from simple annotation services to comprehensive AI data platforms that handle everything from synthetic data generation to model evaluation. The key insight here is that high-quality training data has become as valuable as the models themselves. Model routing represents a fascinating evolution in AI operations. Instead of using one expensive model for everything, routing systems like RC Conductor analyze each request and direct it to the most appropriate model, balancing cost, speed, and quality. Companies are reporting up to 64% cost reductions through intelligent routing. Think of it like a smart traffic management system for AI requests. Simple queries like password resets go to lightweight, fast models. Complex analysis tasks get routed to more powerful systems. The result is dramatically improved cost efficiency without sacrificing quality. The marketplace aspect is equally important. Platforms are emerging where developers can buy and sell prompts, access specialized models, and share optimization techniques. This creates network effects. The more developers participate, the more valuable the platform becomes for everyone.
Let me paint a picture of how these markets interconnect with a real example. Consider a company building a customer support chatbot. They might use Scale AI for initial data labeling, synthetic data platforms to generate edge case scenarios, model routing to optimize cost and performance, and safety evaluation tools to ensure compliance. Each component comes from the different specialized market, but together they create a solution that would have been impossible just 2 years ago.
The implications of these second-order markets extend far beyond individual use cases. We're seeing reduced barriers to entry for AI-powered applications, accelerated innovation cycles, and the emergence of AI-native business models that couldn't exist without these supporting ecosystems. However, there are significant challenges we need to acknowledge. Skills gaps remain substantial. Many organizations struggle to effectively integrate these tools. Ethical safeguards are still evolving, and regulatory frameworks are lagging behind technological capabilities. There's also the risk of over-dependence on synthetic data or automated systems. Quality control becomes critical as these markets scale. When you're building on top of AI-generated content, synthetic data, and automated evaluations, small errors can compound quickly. The most successful implementations combine AI capabilities with human oversight and validation. Looking forward, we can expect these markets to become even more interconnected and sophisticated. Multimodal capabilities will become standard. Imagine seamlessly transitioning from text to image to video to 3D content within a single workflow. Real-time optimization will become the norm, with systems continuously learning and adapting. The geographic distribution of these markets is also worth noting. While the U.S. dominates in foundational models and investment, we're seeing innovative second-order applications emerging globally. European companies are leading in privacy-preserving synthetic data, while Asian markets are driving advances in content creation tools. Enterprise adoption is accelerating rapidly, but it's happening in phases. Companies typically start with low-risk applications like marketing content generation, then gradually expand to more critical functions as confidence and capabilities mature. As we wrap up today's exploration of second-order AI markets, it's clear that we're witnessing the emergence of entirely new economic ecosystems. These markets aren't just supporting the AI industry, they're creating new possibilities for how we create, validate, and deploy AI-powered solutions across every sector of the economy. The key takeaway for tech professionals is that understanding these second-order markets has become essential for building competitive AI applications. Whether you're a developer, product manager, or business leader, these tools and services are likely to become core components of your technology stack. In our next episode, we'll examine how enterprises are actually adopting these technologies in practice. We'll dive into enterprise adoption reality, looking at top-down AI programs, ROI measurement challenges, the shift from CapEx to OpEx spending, and the phenomenon of shadow AI adoption that's happening in organizations worldwide. It's one thing to understand what's possible with these second-order markets, it's another to see how large organizations are actually implementing them at scale.
Until next time, keep connecting the dots in the world of artificial intelligence. The ecosystem effects we've discussed today are just the beginning of a much larger transformation that's reshaping how we think about technology, creativity, and business itself.
Welcome to State of the AI Industry 2025, the podcast where we break down the complex ecosystem of artificial intelligence for tech and software professionals. I'm Steven, your host, and I'm joined by Edith as we explore the layers of this rapidly evolving industry. Today, we're diving into something that's happening right now in boardrooms across the globe, a reality that's both more pragmatic and more complex than the headlines suggest. We're talking about enterprise adoption of AI, but not the theoretical adoption. We're talking about the messy, real-world implementation happening inside large organizations today.
That's right, Stephen. And what makes this particularly fascinating is that we're seeing a dramatic shift from last episode's discussion about second-order markets and generative AI tools. Well, those new ecosystems are creating incredible possibilities for content creation and synthetic data. Today, we're looking at how actual enterprises, the Fortune 500s, the global corporations, are making AI work within their existing structures, their compliance requirements, and their risk tolerance.
Exactly. Today, we'll be examining 4 critical dimensions of this enterprise reality. First, we'll look at the top-down programs that organizations are implementing, the centers of excellence, the steering committees, and the governance frameworks that are becoming the backbone of enterprise AI strategy. Then, we'll dive into the numbers that executives really care about: return on investment, productivity claims, and whether the ROI data actually holds up to scrutiny.
We'll also explore the fascinating economics of AI at enterprise scale, how companies are navigating the shift from traditional capital expenditures to operational expenses, and why a new discipline called FinOps is becoming critical for managing AI costs. But perhaps most intriguingly, we'll examine what I call the shadow adoption phenomenon: employees using AI tools without official approval, and how organizations are responding to this reality.
And we can't ignore the risk dimension. Enterprise leaders are grappling with vendor selection criteria, security requirements, compliance frameworks, and the very real challenges of AI hallucinations and bias in business-critical applications. These aren't theoretical concerns anymore. They're showing up in boardroom discussions and procurement contracts.
What's particularly important to understand is how all of these elements connect to build a complete picture of where AI adoption really stands in 2025. This isn't just about technology anymore. It's about organizational transformation, financial strategy, risk management, and human behavior all colliding in real time.
So let's start with the organizational structure. What are enterprises actually building to manage AI at scale? When I look at the data from companies successfully implementing AI, there's a clear pattern emerging around what they call centers of excellence, or COEs. These aren't just committees, they're operational hubs with real authority and resources.
Think of a center of excellence like the central nervous system of an enterprise's AI efforts. Just as your nervous system coordinates complex movements and processes across your body, a COE coordinates AI initiatives across different business units, ensuring they work together rather than against each other. According to the research, these COEs are typically cross-functional teams that include technical experts, business leaders, legal counsel, and risk management professionals, all working under a unified charter.
The governance structure is fascinating because it's typically 3-layered. At the top, you have steering committees providing strategic oversight and making funding decisions. These are usually C-level executives who set the vision and allocate resources. In the middle, you have the operational COE team that actually implements standards, develops reusable components, and provides technical guidance. And at the bottom, you have the individual business units that own specific use cases and applications.
What I find compelling is how this resembles the hub-and-spoke model we see in other enterprise transformations. The COE is the hub that establishes enterprise-wide standards, governance models, and shared infrastructure. The business units are the spokes that actually deploy AI solutions, but within the guardrails set by the center. This prevents the chaos of everyone building their own AI solutions in isolation, while still allowing for innovation and customization.
And the data shows this approach is working. Companies with formal COEs are seeing more consistent outcomes, better risk management, and faster scaling of successful pilots. They're also better at avoiding what the industry calls pilot purgatory, where organizations run dozens of proof of concepts but never actually deploy anything into production.
Now, let's talk about the numbers that really matter to executives: return on investment. Because all of this organizational structure only makes sense if AI is actually delivering measurable business value. And here's where things get both exciting and concerning.
The claimed benefits are impressive. We're seeing reports of 3.7 times return on investment from some implementations, developer productivity increases of 30%, and significant reductions in support workloads. Companies like JP Chase are reporting 20% reductions in fraud losses, while Walmart has decreased stockouts by 30% through AI-powered supply chain optimization.
But here's the critical nuance. Independent verification of these ROI claims is surprisingly limited. Most of the data comes from either the companies themselves or from vendors with clear financial incentives. It's like asking a real estate agent if now is a good time to buy a house. The answer is predictably optimistic.
That said, the patterns are consistent enough to suggest real value creation. We're seeing productivity gains primarily in two areas: automating routine tasks and augmenting human decision-making. For junior employees, the productivity boost appears to be 20 to 30%, largely because AI can help them perform tasks that previously required senior expertise. For senior employees, the gains are more modest, 10 to 15%, but still significant at enterprise scale.
What's particularly interesting is how companies are measuring success. The most sophisticated organizations aren't just looking at cost savings, they're tracking revenue impact, customer satisfaction improvements, and competitive advantages. Delta Airlines, for example, is seeing an 8% boost in dynamic pricing revenue, not just cost reductions.
But there's a transparency problem. Boards are demanding clear KPIs and measurable outcomes, but many organizations struggle to isolate AI's specific contribution from other business improvements happening simultaneously. It's like trying to measure the impact of a single ingredient in a complex recipe.
This brings us to a fundamental shift in how enterprises think about technology spending. Traditionally, companies would make large capital expenditures, buying servers, software licenses, and infrastructure upfront. But AI is forcing a move toward operational expenditures, where costs are variable and usage-based.
The economics are fascinating. Instead of buying hardware, companies are paying per API call, per token processed, or per user seat. This creates unprecedented flexibility, but also unprecedented unpredictability in costs. A successful AI application might suddenly generate millions of API calls, causing budget overruns that traditional IT planning never anticipated.
It's like switching from owning a car to using ride-sharing services. You gain tremendous flexibility, no maintenance, no depreciation, no parking costs, but your monthly transportation expense becomes variable and potentially unlimited. You could end up spending far more than expected if you start taking long trips or using the service more frequently than planned.
This is why FinOps, financial operations, is becoming critical for AI adoption. FinOps combines financial management with operational efficiency, giving organizations real-time visibility into AI spending and the ability to optimize costs dynamically. Companies are implementing automated controls that can scale AI workloads up or down based on demand and budget constraints.
The data shows that companies allocating more than 5% of their IT budget to AI are seeing 70 to 75% positive ROI, while those spending less than 5% only achieve 50 to 55% positive returns. This suggests there's a minimum threshold for AI investment. You can't just dabble and expect transformative results.
For high-scale deployments, some organizations are moving back toward capital expenditures by building on-premises inference capabilities. This hybrid approach allows them to control costs for predictable workloads while maintaining cloud flexibility for variable demand.
What's particularly interesting is how companies are measuring success. The most sophisticated organizations aren't just looking at cost savings. They're tracking revenue impact, customer satisfaction improvements, and competitive advantages. Delta Airlines, for example, is seeing an 8% boost in dynamic pricing revenue, not just cost reductions.
But there's a transparency problem. Boards are demanding clear KPIs and measurable outcomes, but many organizations struggle to isolate AI's specific contribution from other business improvements happening simultaneously. It's like trying to measure the impact of a single ingredient in a complex recipe.
This brings us to a fundamental shift in how enterprises think about technology spending. Traditionally, companies would make large capital expenditures, buying servers, software licenses, and infrastructure upfront. But AI is forcing a move toward operational expenditures, where costs are variable and usage-based.
The economics are fascinating. Instead of buying hardware, companies are paying per API call, per token processed, or per user seat. This creates unprecedented flexibility, but also unpredictable uncostability in costs. A successful AI application might suddenly generate millions of API calls, causing budget overruns that traditional IT planning never anticipated.
It's like switching from owning a car to using ride-sharing services. You gain tremendous flexibility, no maintenance, no depreciation, no parking costs, but your monthly transportation expense becomes variable and potentially unlimited. You could end up spending far more than expected if you start taking long trips or using the service more frequently than planned.
This is why FinOps, financial operations, is becoming critical for AI adoption. FinOps combines financial management with operational efficiency, giving organizations real-time visibility into AI spending and the ability to optimize costs dynamically. Companies are implementing automated controls that can scale AI workloads up or down based on demand and budget constraints.
The data shows that companies allocating more than 5% of their IT budget to AI are seeing 70 to 75% positive ROI, while those spending less than 5% only achieve 50 to 55% positive returns. This suggests there's a minimum threshold for AI investment. You can't just dabble and expect transformative results.
For high-scale deployments, some organizations are moving back toward capital expenditures by building on-premises inference capabilities. This hybrid approach allows them to control costs for predictable workloads while maintaining cloud flexibility for variable demand.
But perhaps the most fascinating aspect of enterprise AI adoption isn't what's happening in the boardroom, it's what's happening at individual desks across organizations. We're seeing widespread shadow adoption, where employees are using AI tools without official approval or oversight.
The numbers are striking. Research indicates that approximately 50% of employees are using unauthorized AI tools, with 46% saying they would continue using these tools even if explicitly banned by their organizations. This isn't malicious behavior. Employees are simply trying to be more productive and finding AI tools genuinely helpful.
Think of it like water finding its way downhill. People naturally gravitate toward tools that make their work easier, regardless of official policies. Employees are uploading documents to ChatGPT for analysis, using AI writing assistants for emails, or leveraging AI image generators for presentations, often without realizing they might be exposing sensitive company data.
The security implications are significant. When employees paste proprietary information into external AI services, that data often gets incorporated into the service's training data or stored on external servers. It's like having a conversation about confidential business matters in a crowded restaurant. You might not think anyone is listening, but you can't control who overhears or remembers.
Organizations are responding in different ways. Some are taking a restrictive approach, blocking access to AI services through network controls and implementing monitoring tools to detect unauthorized usage. Others are taking an enabling approach, providing enterprise AI accounts, creating internal chatbots with appropriate safeguards, and establishing data classification systems that help employees understand what information is safe to share with AI tools.
The most sophisticated organizations are treating shadow AI as a signal rather than a problem. If employees are gravitating towards certain AI capabilities, that indicates genuine business value that should be captured through official channels rather than eliminated through prohibition.
This brings us to the critical question of vendor selection and risk management, because whether it's official procurement or shadow adoption, enterprises are ultimately dependent on AI vendors whose capabilities and reliability vary dramatically.
The vendor evaluation criteria have evolved far beyond traditional technology assessments. Security and compliance capabilities are now paramount. Organizations need to understand how vendors handle data, where that data is stored, whether it's used for training, and what happens if there's a breach or service interruption.
It's like hiring a contractor to work on your house. You're not just evaluating their technical skills, you're also assessing their insurance, their reputation, their reliability, and whether you trust them with access to your property. With AI vendors, that trust extends to your most sensitive business data and critical operational processes.
Integration capabilities are equally important. AI tools that can't integrate with existing enterprise systems create data silos and workflow disruptions. Organizations are prioritizing vendors that offer robust APIs, support single sign-on authentication, and can work within existing security frameworks.
Service-level agreements for AI are particularly complex because traditional uptime metrics don't capture the full picture. An AI service might be technically available, but performing poorly due to model degradation, training data issues, or capacity constraints. Organizations are learning to negotiate SLAs that include accuracy metrics, response time guarantees, and performance benchmarks.
But the risks extend beyond technical performance. AI systems can generate biased outputs, hallucinate false information, or produce content that violates regulatory requirements. These aren't edge cases, they're predictable behaviors that enterprises must plan for.
The hallucination problem is particularly insidious because AI-generated content can be very convincing even when it's completely wrong. It's like having an extremely confident assistant who occasionally gives you completely fabricated information but delivers it with such authority that you don't question it.
Organizations are implementing several mitigation strategies. Retrieval-augmented generation systems ground AI outputs in verified enterprise data. Human-in-the-loop processes ensure critical decisions still have human oversight. And citation requirements force AI systems to provide sources for their claims, making it easier to verify accuracy.
Risk taxonomies are becoming standard tools for categorizing and managing AI-related risks. These frameworks typically cover strategic risks around business alignment, financial risks from implementation costs, operational risks from system failures, compliance risks from regulatory violations, technological risks from security vulnerabilities, reputational risks from public incidents, ethical risks from bias decisions, and human capital risks from workforce displacement.
What's particularly interesting is how these risks interconnect. A technical failure might create operational disruption, which could lead to compliance violations, resulting in reputational damage and financial penalties. Enterprise risk management for AI requires thinking systemically about these cascading effects.
The regulatory landscape is also evolving rapidly. The EU AI Act creates specific compliance requirements for high-risk AI applications. In the United States, executive orders and federal guidance are establishing standards for government AI procurement that often influence private sector practices. Organizations need vendors who understand and can help navigate this complex regulatory environment.
Looking at the patterns emerging from successful enterprise AI adoption, several themes become clear. First, organizational structure matters. Companies with formal governance frameworks and centers of excellence are outperforming those with ad hoc approaches. Second, financial discipline is critical. Organizations need sophisticated cost management and ROI measurement capabilities to succeed with AI at scale.
Third, the human element is crucial, both in terms of managing shadow adoption and ensuring appropriate human oversight of AI systems. And fourth, risk management can't be an afterthought. Successful organizations are building comprehensive frameworks for evaluating vendors, managing technical risks, and ensuring compliance with evolving regulations.
What makes this particularly complex is that all of these elements must work together. You can't just implement good governance without also having financial controls. You can't manage technical risks without understanding the human factors. And you can't optimize for today's requirements without planning for tomorrow's regulatory changes.
As we look toward our next episode, these enterprise adoption patterns are setting the stage for significant workforce restructuring. The productivity gains and operational changes we've discussed today are already influencing hiring decisions, role definitions, and skills requirements across industries. We'll explore specific examples of how organizations are managing workforce transformation, from layoffs justified by AI efficiency to upskilling programs designed to help employees work alongside AI systems.
That's right. The reality of enterprise AI adoption is creating ripple effects throughout the job market, and understanding these workforce impacts is crucial for both business leaders and individuals navigating this transformation.
Thanks for joining us for this deep dive into enterprise AI adoption reality. Until next time, keep connecting the dots in the world of artificial intelligence.
We'll see you next time on State of the AI Industry 2025. Welcome to State of the AI Industry 2025, where we're connecting the dots in the rapidly evolving world of artificial intelligence. I'm Stephen.
And I'm Edith. Today, we're diving into one of the most complex and emotionally charged aspects of the AI revolution, how it's reshaping the workforce, not through abstract predictions, but through real stories happening right now.
If you've been following our series, we've explored everything from foundational hardware to enterprise adoption patterns. In our last episode, we examined how companies are implementing AI governance frameworks and calculating ROI on their AI investments. But what we haven't addressed yet is perhaps the most human element of this transformation. What happens to the people whose jobs are being redefined or eliminated by the very technology they helped build?
Exactly. We're at a fascinating inflection point where we can observe actual workforce restructuring happening in real time. Today, we'll examine specific cases of layoffs attributed to AI efficiency gains, explore innovative retraining programs that are actually working, and analyze the regulatory and ethical considerations that are starting to emerge.
And we'll ground this in hard data from organizations like the IMF, which recently projected that 40% of global employment will be exposed to AI, with some predicting displacement risks for about 20% of workers. But before we get into the theoretical frameworks, let's start with what's happening right now in boardrooms across America and beyond.
The stories we're seeing aren't just numbers on spreadsheets. Take Amazon CEO Andy Jassy, who in June 2025 sent an email that sent shockwaves through the tech industry. He explicitly stated that AI deployment will reduce Amazon's total corporate workforce over the next few years through efficiency gains from using AI extensively. This wasn't corporate speak about optimization. It was a direct acknowledgement that fewer people will be needed to do the same work.
What makes Jassy's announcement particularly significant is its departure from the prevailing narrative we've heard for years about AI as workforce augmentation. Instead of the collaborative human-AI partnership story, we're seeing a clear shift toward direct job replacement strategy. Amazon's 350,000 corporate employees face the greatest vulnerability to AI automation compared to warehouse workers, ironically because their cognitive tasks are more easily replicated by current AI systems.
Think of it like a river changing course. For decades, companies have been flowing along one narrative stream, that technology would enhance human capabilities, make us more productive partners in the workplace. But now we're witnessing this dramatic redirect, where the river is carving an entirely new path through the employment landscape.
Salesforce provides another compelling case study. Mark Benioff revealed that the company cut 4,000 customer support jobs, reducing their support workforce from 9,000 to 5,000. But here's what's particularly interesting from a technical perspective. AI agents now handle approximately 1.5 million conversations and roughly 30 to 50% of support tasks. The company claims they've achieved this while maintaining customer satisfaction through what they call a supervisor framework.
What's striking about the Salesforce example is the precision with which they've measured the transition. They're not just throwing AI at the problem and hoping for the best. They've created a systematic approach where AI handles the routine, predictable interactions while humans focus on complex problem solving. It's like having a triage system in an emergency room. AI handles the straightforward cases, freeing up skilled humans for situations that require empathy, creativity, and complex reasoning.
The pattern becomes even more pronounced when we look at Fiverr, which announced a 30% workforce reduction, about 250 people, as part of what CEO Micah Kaufman calls becoming an AI-first company. What's particularly telling is that Fiverr's revenue is still growing at 8 to 12%, but they're plateauing in terms of acquiring new users. So AI becomes the solution to maintain growth while reducing costs.
The Fiverr situation illustrates a broader shift in the gig economy itself. It's no longer about cheap labor at scale. It's automation, efficiency, and extracting more value from existing users. For freelancers, this creates a double-edged sword. The platform that connects them to work is simultaneously automating away simpler gigs that many freelancers depend on for steady income.
Indeed and Glassdoor present another fascinating data point. These job hunting platforms, ironically the very companies people turn to when looking for work, cut approximately 1,300 jobs. CEO Hisayuki Ida Koba was remarkably direct, stating that AI is changing the world and we must adapt. He noted that about 1/3 of their new programming code is now generated by AI, and he expects that figure to reach 50.
There's something almost poetic about job search platforms laying off workers due to AI, isn't there? It's like the tools we use to find work are being optimized by the same technology that's eliminating work. But what's interesting is how these companies are framing the transition. They're not just cutting costs, they're arguing they need to fundamentally restructure how they deliver value to both job seekers and employers.
Microsoft and Google represent a different category. They're simultaneously cutting jobs while making massive AI investments. Microsoft eliminated over 15,000 positions while investing $80 billion in AI infrastructure. The company reports saving over $500 million through AI integration in customer service and sales functions alone. What's particularly noteworthy is that CEO Satya Nadella reveals AI now writes 20–30% of Microsoft's code.
This creates what I call the reinvestment paradox. Companies are using human employees to build and train AI systems that will eventually replace those same employees. It's like asking someone to train their own replacement, except the replacement doesn't need health insurance, vacation time, or career development opportunities. The humans are literally teaching the machines how to make them redundant.
But here's where the story becomes more nuanced, and this is crucial for understanding the full picture. Not every company is choosing the layoff route. IKEA provides a compelling counter-narrative. When they introduced an AI chatbot called Billy that handled 47% of customer inquiries, they didn't eliminate their call center staff. Instead, they retrained 8,500 employees to become interior design advisors.
IKEA's approach is fascinating because it demonstrates that technology and people don't have to be in competition. They recognize that while AI could handle routine customer service queries, there were still numerous areas where human expertise was not just valuable, but essential. Think of it as job evolution rather than job elimination, like how bank tellers didn't disappear when ATMs were introduced, but their roles evolved to focus on more complex financial services and relationship building.
The financial impact of IKEA's strategy was remarkable. They reported an unexpected $1.4 billion in additional revenue from these new interior design services. This suggests that strategic reskilling can actually unlock new revenue streams rather than simply cutting costs. The key insight is that they built upon employees' foundational customer service knowledge rather than starting from scratch.
What IKEA understood is that certain human capabilities, empathy, creative problem solving, the ability to understand nuanced customer needs and preferences, these aren't just difficult to replicate with AI, they're actually becoming more valuable as AI handles the routine tasks. It's like pruning a tree. When you remove the routine branches, the human skills that remain can grow stronger and more valuable.
Accenture presents another interesting model. Rather than mass layoffs, they're implementing what CEO Julie Sweet calls rapid talent rotation. They're actively exiting employees who cannot be reskilled for AI, while simultaneously expanding their AI talent pool to 77,000 data and AI professionals. They've trained over 550,000 employees in generative AI fundamentals.
Accenture's approach recognizes a fundamental reality about the AI transition. It's not just about replacing humans with machines, it's about reconfiguring the entire workforce around new capabilities. Some employees can make this transition, others cannot, and the company needs different skills for the future. It's brutally practical, but also more honest than companies that promise everyone can be retrained while quietly planning layoffs.
This brings us to the broader economic implications. The IMF's analysis suggests that 40% of global employment will be exposed to AI, with advanced economies facing higher exposure rates, about 60%, compared to emerging markets at 40% and low-income countries at 26%. The key finding is that roughly half of the exposed jobs may benefit from AI integration, while the other half faces potential displacement.
The IMF data reveals something crucial about the nature of this transition. It's not uniformly distributed across the global economy. Advanced economies with their emphasis on cognitive work and service industries are most vulnerable because those are precisely the tasks that current AI excels at automating. It's counterintuitive. We always assumed automation would come from manual labor first, but AI is actually more capable of replacing knowledge workers than physical laborers.
What makes this particularly complex from a policy perspective is the speed of the transition. Previous technological disruptions, like the Industrial Revolution or the advent of personal computers, typically gave societies years or decades to adapt. But AI's capabilities are advancing so rapidly that workers may need to begin adapting within the next 1 to 2 years, not decades.
This compression of the adaptation timeline is where the regulatory and ethical considerations become critical. We're seeing the emergence of policy proposals like robot taxes. The idea that companies deploying automation should pay taxes on those machines similar to payroll taxes on human workers. Bill Gates has been a prominent advocate, arguing that if a human earning $50,000 is taxed, why shouldn't a robot performing the same role face similar taxation?
The robot tax concept addresses several policy challenges simultaneously. First, it could help maintain government tax revenues as payroll tax collections decline due to workforce automation. Second, it could fund retraining programs for displaced workers. Third, it might slow the pace of automation slightly, giving communities more time to adapt. However, critics argue it could stifle innovation and make countries less competitive globally.
Think of robot taxes like environmental regulations. They're attempting to internalize the social costs of automation that are currently externalized onto society. When a company automates jobs, they capture the efficiency benefits, but society bears the costs of unemployment, retraining, and social disruption. A robot tax would force companies to account for some of these broader social impacts in their automation decisions.
The regulatory landscape is becoming increasingly complex as governments grapple with these challenges. There's growing public scrutiny of AI-related layoffs, with some companies facing brand reputation risks when their workforce reduction strategies become public. Companies are having to balance efficiency gains against potential backlash from customers, employees, and communities.
We're also seeing interesting variations in how different leaders are framing the future of work. Some, like Elon Musk, predict scenarios where AI could potentially handle most jobs, requiring fundamental restructuring of economic systems. Others, like NVIDIA's Jensen Huang, emphasize the importance of human-AI collaboration. The European Union has taken a different approach, focusing on how AI can enhance human capabilities rather than replace them entirely.
What's emerging is a recognition that this isn't just a technological transition. It's a social and economic transformation that requires coordinated responses from business, government, and educational institutions. Some companies are proactively investing in education and retraining programs, recognizing that their long-term success depends on having a skilled workforce that can work alongside AI systems.
The education component is crucial and often overlooked. It's not enough to retrain workers for current AI tools. We need to prepare people for a future where the nature of work itself continues to evolve. This means developing meta skills like learning how to learn, adapting to new technologies quickly, and focusing on uniquely human capabilities that complement rather than compete with AI.
As we look ahead, the patterns we're seeing today will likely accelerate and become more pronounced. Companies that successfully navigate this transition will be those that can balance efficiency gains from AI with strategic investment in human capital. Those that view it purely as a cost-cutting exercise may find themselves at a competitive disadvantage as the importance of human-AI collaboration becomes clearer.
The workforce restructuring stories we're witnessing today are really the opening chapters of a much longer transformation. Companies like IKEA and Accenture are showing us that there are multiple pathways through this transition. Some focus on reskilling and job evolution, others on strategic workforce rotation, and unfortunately, some simply on cost reduction. The choices organizations make today will shape not just their own futures, but the broader social contract between technology and employment.
What's particularly important for our listeners to understand is that this isn't a distant future scenario. It's happening right now. The decisions being made in boardrooms today about AI implementation, workforce strategy, and employee development are creating the employment landscape of tomorrow. Whether that landscape is characterized by widespread displacement or strategic human-AI collaboration depends largely on the choices we make in the next few years.
And that brings us to our next episode, where we'll shift our focus from the corporate level to the policy level. We'll explore how different governments around the world are responding to these workforce challenges through regulation, investment strategies, and international cooperation. From the U.S. executive orders on AI development to China's state-led AI strategy, from the European Union's risk-based regulatory framework to emerging policies in the Middle East and Asia, the geopolitical dimensions of AI are shaping how these workforce transitions will unfold globally.
That's right. While companies are making individual decisions about automation and workforce strategy, governments are grappling with the broader implications for national competitiveness, social stability, and international relations. Join us next time as we examine how geopolitics and regulation are influencing the future of AI development and deployment worldwide. Welcome to State of the AI Industry 2025, where we decode the forces shaping artificial intelligence for tech and software professionals. I'm Stephen.
And I'm Edith. Today we're exploring a fascinating intersection where technology meets geopolitics, how nations worldwide are crafting AI policies that could determine the global balance of technological power for decades to come.
In our previous episode, we examined the human impact of AI, the workforce restructuring, the layoffs disguised as efficiency gains, and the scramble to retrain millions of workers. But here's the thing, those workforce transformations aren't happening in isolation. They're unfolding against a backdrop of intense geopolitical maneuvering, where every regulation, every visa policy, and every trade restriction is a strategic move in a global chess game for AI supremacy.
Exactly. Today we're diving into 5 critical dimensions of this geopolitical landscape. First, we'll examine how major powers like the US, China, and the EU are taking dramatically different regulatory approaches. From America's deregulation push under Executive Order 14179 to China's state-controlled pre-approval system and Europe's Comprehensive AI Act. Then we'll explore the UK's lighter touch strategy with their newly rebranded AI Security Institute and how Middle Eastern nations and Asia-Pacific countries are positioning themselves as AI investment hubs.
We'll also unpack the fascinating dynamics of trade and talent flows, how export controls are reshaping chip supply chains, how countries are weaponizing visa policies to attract AI researchers, and why hyperscale data centers are becoming the new battlegrounds for technological influence. These aren't just policy details, they're the foundational infrastructure decisions that will determine which nations can build, deploy, and control the next generation of AI systems.
Think of it this way. If our previous episode showed us how AI is restructuring the workforce within companies, today we're zooming out to see how entire nations are restructuring their policies to either accelerate or control AI development. These regulatory frameworks are the invisible hand shaping where innovation happens, where talent flows, and ultimately where economic and strategic power concentrates in the AI age.
Let's start with the United States, where the Trump administration's Executive Order 1479 in January 2025 marked a dramatic pivot from the previous Biden approach. This order, titled Removing Barriers to American Leadership in Artificial Intelligence, essentially reversed the comprehensive safety framework that Biden had established with Executive Order 1410 back in October 2023.
The shift is remarkable when you consider what Biden's framework included: mandatory safety testing for large models, extensive reporting requirements, and what the industry saw as burdensome compliance measures. Trump's approach essentially said, we're going to win this race by getting government out of the way. The new executive order mandates the creation of an AI action plan within 180 days, focusing purely on maintaining U.S. dominance through deregulation and private sector innovation.
And that action plan, released in July 2025 as Winning the Race, America's AI Action Plan, crystallizes this philosophy into 3 pillars: accelerating innovation, building infrastructure, and leading in international diplomacy and security. But here's what's fascinating. While the U.S. is deregulating domestically, it's simultaneously tightening export controls on AI chips to China. It's essentially creating maximum freedom at home while restricting competitors abroad.
That's the key contradiction worth understanding. The U.S. strategy assumes that unrestricted domestic development will maintain technological security, while export controls will slow competitors. But this creates what economists call a control paradox. The more you restrict others, the more incentive you give them to develop alternatives. And we're already seeing this play out with China's domestic chip development and innovative approaches like DeepSeek's models.
Speaking of China, their approach couldn't be more different. The Chinese regulatory framework, anchored by the interim measures for the management of generative artificial intelligence services that took effect in August 2023, represents state-directed AI development with comprehensive pre-approval requirements.
China's model is fascinating because it treats AI as critical infrastructure that requires state oversight at every level. Any generative AI service offered to the public in China, whether from domestic or foreign companies, must undergo security assessments, content moderation reviews, and algorithm transparency requirements. It's like having a building inspector approve every floor of a skyscraper before construction can proceed to the next level.
The practical implications are enormous. Where a U.S. company like OpenAI can launch a new model with minimal regulatory friction, a Chinese company must demonstrate compliance with data localization requirements, prove their training data doesn't infringe on intellectual property rights, and establish mechanisms for content labeling and user complaint handling. This creates a completely different innovation timeline and cost structure.
But here's what's clever about China's approach. While it appears restrictive, it's actually creating a protected domestic market for AI development. Foreign companies face the same regulatory hurdles as domestic ones, but Chinese companies have the advantage of understanding the regulatory landscape and building compliance into their development processes from day one. It's like requiring everyone to play by house rules, but giving the home team the rulebook in advance.
The data localization component is particularly strategic. By requiring AI companies to process Chinese user data within China's borders, they're essentially forcing global AI companies to either build Chinese data infrastructure, creating dependencies and vulnerabilities, or exit the Chinese market entirely, leaving space for domestic competitors to flourish.
Now let's contrast this with the European Union's AI Act, which represents perhaps the most comprehensive attempt at risk-based AI regulation globally. The EU AI Act, which became fully applicable in August 2024, takes what I'd call an engineering approach to AI governance, categorizing AI systems by risk level and applying proportionate regulatory requirements.
The EU framework is sophisticated in ways that both the US and Chinese approaches miss. Instead of blanket deregulation or state control, the AI Act creates a taxonomy: prohibited AI uses like social scoring systems, high-risk applications like hiring and loan approval that require extensive testing and documentation, and general-purpose AI models above certain compute thresholds that face systemic risk obligations.
What's particularly innovative is how the EU handles general-purpose AI models, what we call foundation models like GPT-4 or Claude. Providers of GPAI models with systemic risk must conduct model evaluations, assess and mitigate risks, report serious incidents, and ensure cybersecurity measures. But here's the crucial detail. The EU published a voluntary code of practice that allows companies to demonstrate early compliance while the full regulatory framework phases in.
This creates what regulators call a compliance runway. Companies can start adapting their practices now using the voluntary framework rather than facing a cliff-edge compliance requirement. And because the AI Act has extraterritorial effects, meaning any AI system sold in the EU must comply regardless of where it's developed, this is essentially setting global standards through market access requirements.
Think of the EU approach like automotive safety standards. Just as cars sold anywhere in the world often meet the highest safety requirements of any major market they're sold in, AI systems are increasingly being designed to meet EU AI Act requirements even if they're primarily deployed elsewhere. This gives the EU enormous indirect influence over global AI development practices.
The UK presents yet another model, what they're calling a lighter touch approach, centered around their AI Safety Institute, which was notably rebranded as the AI Security Institute in February 2025. This name change signals a shift from broad AI safety concerns to focusing specifically on security implications of frontier AI systems.
The UK strategy is interesting because it's trying to thread a needle between innovation and oversight. Rather than comprehensive legislation like the EU, they're building institutional capability for AI evaluation and testing while maintaining regulatory flexibility. The AI Security Institute has successfully conducted pre-deployment testing of major models, including Google's Gemini Ultra and OpenAI's O1 model.
But here's the UK's strategic challenge. They're building evaluation capability without enforcement power. The AI Security Institute can test models and identify risks, but they can't compel companies to address those risks or prevent model deployment. It's like health inspectors who can examine restaurants but can't close them down or require fixes.
That's where international cooperation becomes crucial. The UK has signed agreements with the US AI Safety Institute, now called the Center for AI Standards and Innovation, to jointly test advanced AI models and share research insights. They're essentially trying to build influence through expertise and partnerships rather than regulatory authority.
Moving beyond the major powers, we're seeing fascinating developments in the Middle East and Asia-Pacific. Saudi Arabia, through their Vision 2030 framework and the $14.9 billion investment announced at LEAP 2025, is positioning itself as a regional AI hub with massive infrastructure investments and partnerships with companies like NVIDIA, AMD, and AWS.
Saudi Arabia's Humane initiative is particularly ambitious. They're aiming to manage 7% of global AI workload by 2030 through a combination of advanced data centers, Arabic language models, and a $10 billion venture fund for AI startups worldwide. It's like they're building AI infrastructure as a new form of energy export. Instead of selling oil, they're selling compute capacity and AI services.
The UAE is taking a similar but distinct approach. Their National AI Strategy 2031, backed by a $100 billion MGX fund, includes nationwide access to ChatGPT Plus for all residents and partnerships with NVIDIA to build AI factories, massive AI computing infrastructure serving the Middle East and Africa. They're positioning themselves as the regional gateway for AI services.
India represents perhaps the most interesting talent-focused strategy. According to the Stanford AI Index 2024, India leads globally in AI skill penetration with a score of 2.8, and their AI talent concentration has grown by 263% since 2016. Rather than competing primarily on infrastructure or regulation, India is building advantage through human capital development.
India's Future Skills Prime initiative, led by the Ministry of Electronics and Information Technology, focuses on reskilling the existing IT workforce in AI technologies while building new AI talent through premier institutions. They're essentially treating AI talent development as industrial policy, systematically building the human infrastructure needed for AI competitiveness.
Now let's examine how these different regulatory approaches are creating global flows of trade and talent that are reshaping the competitive landscape. The U.S. export controls on advanced semiconductors to China, which began in earnest in October 2022 and have been repeatedly strengthened, represent one of the most significant interventions in global technology supply chains we've ever seen.
The semiconductor export controls are fascinating because they're trying to achieve multiple objectives simultaneously. First, they're restricting China's access to the most advanced AI chips like NVIDIA's H100 and A100 series. Second, they're preventing the export of chip-making equipment that would allow China to manufacture these chips domestically. And third, they're even prohibiting U.S. persons from supporting advanced Chinese chip facilities.
But here's where it gets complex. These controls are driving exactly the innovation they're trying to prevent. Chinese companies like DeepSeek have demonstrated that they can create competitive AI models using significantly fewer computational resources than their Western counterparts. When you restrict someone's access to powerful hardware, you incentivize them to become more efficient with the hardware they have access to.
The effectiveness question is crucial and depends heavily on timelines. If transformative AI capabilities emerge within 2 to 3 years, as some leaders like Anthropic's Dario Amodi predict, then export controls might successfully limit China's ability to deploy advanced AI at scale. But if significant AI advancements take a decade or more, China will likely develop domestic chip manufacturing capabilities during that time frame, making current controls counterproductive.
Meanwhile, countries are increasingly using immigration policy as an AI competitiveness tool. Canada's global talent stream processes work permits for highly skilled tech workers in as little as 2 to 4 weeks and provides a straightforward path to permanent residency. They're essentially treating visa processing speed as economic infrastructure.
The contrast is stark when you consider recent U.S. policy changes. The Trump administration's proposed $100,000 fee for H-1B visas represents a massive increase from the previous $5,000 fee. For context, the H-1B program has historically been crucial for AI talent. Leaders like Google's Sundar Pichai and Microsoft's Satya Nadella both entered the U.S. through H-1B visas.
Singapore, Switzerland, and other countries are similarly streamlining their immigration processes for AI talent. Singapore's EntrePass program and various AI-focused visa categories create what economists call talent arbitrage opportunities, when immigration barriers in one country create opportunities for others to attract the same talent pool.
This creates a fascinating dynamic where immigration policy becomes industrial policy. Countries that can attract and retain AI researchers and engineers gain competitive advantages not just in AI development, but in the broader ecosystem of companies and applications that develop around AI capabilities.
The infrastructure dimension is equally critical and often overlooked. Hyperscale data centers, the massive facilities that power AI training and deployment, are becoming geopolitical assets. The United States currently accounts for 54% of total worldwide hyperscale data center capacity, with Europe and China each representing about a third of the balance.
But the growth patterns are telling. McKinsey analysis suggests that demand for AI-ready data center capacity will rise at an average rate of 33% per year between 2023 and 2030. Companies like Microsoft are investing $80 billion in fiscal 2025 specifically for AI-enabled data centers, with over half targeted for U.S. infrastructure.
What makes this geopolitically significant is that data center location determines where AI models can be trained, where they're hosted, and which jurisdictions have access to the computational resources needed for advanced AI development. Countries without significant hyperscale infrastructure become dependent on others for AI capabilities.
The energy requirements are staggering and create new dependencies. AI data centers require 50 to 100 kilowatts per rack versus 10 to 15 kilowatts for traditional computing. This means that AI competitiveness increasingly depends on access to reliable, large-scale electricity generation, creating new linkages between energy policy and technological competitiveness.
We're also seeing the emergence of what industry analysts call AI infrastructure partnerships that blur traditional geopolitical lines. The UAE's partnerships with U.S. companies like NVIDIA and OpenAI, Saudi Arabia's collaborations with Google Cloud and Qualcomm, and similar arrangements create interdependencies that don't neatly map on to traditional alliance structures.
These partnerships are interesting because they often involve technology transfer, data localization requirements, and shared governance structures that give host countries significant influence over AI infrastructure within their borders. It's not just about buying services, it's about building local AI capabilities through international partnerships.
Looking at the bigger picture, what we're witnessing is the emergence of distinct AI governance models that reflect different national priorities and capabilities. The U.S. model prioritizes private sector innovation with minimal regulatory friction domestically, while using export controls and international pressure to maintain competitive advantages.
China's model emphasizes state oversight and domestic market protection while building indigenous AI capabilities across the full technology stack. The EU model focuses on rights-based regulation and risk management, while using market access as leverage to influence global AI development practices.
And then we have what we might call hub models from countries like the UAE, Saudi Arabia, and Singapore, which are using strategic investments and favorable policies to position themselves as regional centers for AI development and deployment without necessarily building indigenous AI capabilities at the same scale as the major powers.
The talent competition dimension adds another layer of complexity. Countries like India are building competitive advantages through human capital development, while countries like Canada and Singapore are using immigration policy to attract talent developed elsewhere. This creates brain circulation patterns that can shift competitive balances relatively quickly.
What's particularly fascinating is how these different approaches create both complementary relationships and direct competition simultaneously. For example, Saudi Arabia's AI infrastructure investments complement U.S. AI companies' need for global deployment capabilities, while also potentially reducing dependence on U.S.-controlled infrastructure over time.
The timing of these policy choices matters enormously because AI capabilities are advancing so rapidly. Regulatory frameworks designed for today's AI systems may be obsolete by the time they're fully implemented. This creates what policy scholars call regulatory lag, the gap between technological capability and governance frameworks.
That's why we're seeing experimentation with adaptive regulatory approaches. The EU's voluntary code of practice, the UK's institutional capability building, and various regulatory sandboxes represent attempts to create governance frameworks that can evolve with the technology rather than being locked in to static requirements.
The export control dynamics are particularly complex because they're trying to slow competitors while avoiding harming domestic companies or allies. The challenge is that AI supply chains are globally distributed, so restrictions at any point can have unintended consequences throughout the ecosystem.
And we're starting to see those unintended consequences play out. Chinese companies are developing more resource-efficient AI approaches, partly in response to hardware restrictions. European companies are building compliance capabilities that may give them advantages in regulated markets. Countries excluded from certain partnerships are developing alternative arrangements.
The data center infrastructure competition is especially critical because it has such long lead times. Building hyperscale AI infrastructure takes years and requires enormous capital investments. Countries that don't start building this infrastructure now may find themselves permanently dependent on others for AI capabilities.
But there's also an interesting sustainability angle emerging. The massive energy requirements of AI infrastructure are creating tensions between AI ambitions and climate commitments. Countries that can solve the energy efficiency challenge for AI infrastructure may gain significant competitive advantages.
As we look toward the future, several trends seem clear. First, the regulatory approaches we're seeing now, from US deregulation to Chinese state control to EU risk-based regulation, will likely influence AI development for decades because they're shaping the institutional frameworks and industry practices that will be difficult to change later.
Second, the talent competition is intensifying and becoming more sophisticated. Countries are not just competing for individual researchers, but for entire AI ecosystems, the companies, universities, investors, and supporting industries that create environments where AI innovation thrives.
Third, infrastructure is becoming destiny in AI. Countries that build advanced AI infrastructure now will have advantages that compound over time, while those that don't may find themselves permanently relegated to secondary roles in the global AI ecosystem.
The geopolitical implications extend far beyond technology policy. AI capabilities are increasingly seen as critical to national security, economic competitiveness, and social governance. The countries and regions that get their AI policies right now may determine the global balance of power for the next several decades.
What's particularly striking is how these policy choices are creating different pathways to AI competitiveness. There's no single model that guarantees success, but there are policy combinations that seem more likely to create sustainable advantages in AI development and deployment.
And the window for making these foundational choices may be closing. As AI capabilities advance and become more entrenched in existing systems, it becomes harder to change course or catch up. The decisions being made now about regulation, infrastructure, and talent development may be irreversible in practical terms.
For tech and software professionals, understanding these geopolitical dynamics is crucial because they're shaping the environment in which AI development happens. Whether you're building AI systems, working for companies that deploy them, or making career decisions in the field, these policy frameworks will influence your opportunities and constraints.
The key insight is that AI development isn't happening in a policy vacuum. Every algorithm, every model deployment, every career move in AI is happening within regulatory frameworks and geopolitical contexts that are rapidly evolving. Staying ahead in AI requires understanding not just the technology, but the policy environment shaping how that technology can be developed and deployed.
Next time on State of the AI Industry 2025, we'll shift our focus to the future, exploring where the smart money is going in AI investment. We'll examine the emerging frontiers, from generalist world models that can simulate entire 3D environments to the explosion in robotics and embodied AI to the race for edge computing and neuromorphic architectures.
We'll also dive into the fascinating world of synthetic data and simulation, the rise of neurosymbolic AI architectures that combine neural networks with logical reasoning, and the critical investments being made in AI safety and alignment. These aren't just technical trends, they're the areas where billions of investment dollars are flowing and where the next generation of AI capabilities will emerge.
Until next time, keep connecting the dots in the world of artificial intelligence. Welcome to our final episode of State of the AI Industry 2025. I'm Steven, and today we're closing out this comprehensive journey through the AI landscape by looking ahead to what's next. Throughout this series, we've explored everything from the foundational hardware powering AI to the complex geopolitical forces shaping policy around the globe. Now, as we stand at the threshold of 2026, we need to examine where the smart money is going, the investment frontiers that will define the next phase of artificial intelligence development.
Exactly. And what's fascinating is how these investment frontiers aren't just about throwing money at the latest shiny technology. They represent a fundamental shift in how we think about AI's role in the world. We're moving beyond the pure computational race we've been tracking through previous episodes, the battle for more parameters, faster chips, and bigger data centers, into something much more nuanced. The investment patterns we're seeing in 2025 point toward AI that doesn't just process information, but actively engages with and shapes the physical world around us.
That's a crucial distinction. If we think back to our previous episode on geopolitics and regulation, we saw how different regions are positioning themselves within the existing AI paradigm. But the investment frontiers we're exploring today suggest we're on the cusp of an entirely new paradigm. We're talking about generalist world models that can simulate entire environments, robotic systems that learn by watching humans, neuromorphic computing that mimics brain architecture, and synthetic data generation that could solve the data scarcity problem that's been limiting AI development.
These aren't isolated trends either. They're deeply interconnected, forming what we might call the next layer of the AI stack. Today, we'll examine 6 key investment areas: generalist world models, robotics and embodied AI, edge and neuromorphic computing, synthetic data and simulation, neurosymbolic architectures, and safety evaluation systems. We'll also hear from industry leaders like Andrew Ng, Satya Nadella, and Jensen Huang about where they see the biggest opportunities and risks.
Let's start with what might be the most fundamental shift: generalist world models. These aren't just improved versions of large language models. They represent a completely different approach to AI intelligence. Instead of learning patterns from text and images, world models learn the underlying physics, causality, and dynamics of environments. Think of it as the difference between an AI that has read every cookbook ever written versus one that actually understands how ingredients interact, how heat changes molecular structures, and how timing affects outcomes.
The analogy I like to use is comparing a scholar who has memorized every map in the world to an explorer who actually understands terrain, weather patterns, and navigation. Recent breakthroughs like Google DeepMind's Genie demonstrate interactive 3D world generation that goes far beyond static image or text creation. These models can generate entire virtual environments where cause and effect operate according to realistic physical laws. But here's what makes this particularly significant for investors. World models aren't just academically interesting. They're the foundation for the next generation of AI applications.
The theoretical foundation for this shift is actually quite profound. Research from Google DeepMind has shown that any AI agent capable of generalizing across complex, goal-directed tasks must have learned an accurate predictive model of its environment. This isn't just beneficial, it's mathematically necessary for true general intelligence. What this means is that the path to artificial general intelligence doesn't run through ever larger language models, but through systems that build internal simulations of the world.
And the investment implications are enormous. We're looking at a market that some analysts estimate could be worth up to $100 trillion, essentially the size of the global economy, if we can create intelligence that truly understands and operates in the physical world. The companies and research groups that crack the world model problem won't just have a competitive advantage, they'll have redefined what AI can do. NVIDIA's new Cosmos framework, announced at CES 2025, represents exactly this kind of foundational investment in physical AI infrastructure.
This connects directly to our second major investment frontier, robotics and embodied AI. For decades, robotics has been the promise that always seemed just out of reach. But the convergence of world models, vision language action foundation models, and improved hardware is creating what industry experts call the embodied AI moment. We're not talking about incremental improvements to existing industrial robots, but about general-purpose systems that can operate in human environments.
The numbers here are striking. Robotics funding grew five-fold from 2022 to 2024, surpassing $1 billion in annual investment. Companies like Figure AI, Skyled AI, and Agility Robotics have raised hundreds of millions. Agility, for instance, plans to scale from 1,200 robots in 2025 to 7,500 by 2027. But what's really changed isn't just the funding, it's the underlying technology stack. Modern robots can learn by observing humans, understand spoken instructions, and navigate unstructured environments without being programmed for every specific task.
The breakthrough here is the integration of large language models with robotic control systems. Think of it as giving robots not just better sensors or actuators, but actual understanding. A robot today can be told, "Clean up the living room," and figure out what that means in context, identifying toys that belong on a toy box, magazines that go on a shelf, and cushions that need to be arranged on a couch. This level of contextual understanding was impossible with previous approaches that required explicit programming for every scenario.
And this is where the investment thesis becomes compelling. Unlike previous waves of robotics development that focused on specific industrial applications, we're seeing a shift toward platforms that can handle multiple use cases. It's like the difference between building a calculator for each mathematical operation versus building a computer that can run any software. The total addressable market expands dramatically when you're not just replacing human workers in one specific task, but creating systems that can adapt to entirely new challenges.
Our third investment frontier takes us in a different direction: edge and neuromorphic computing. While much of the AI industry has focused on building larger and larger data centers, there's a growing recognition that we need AI that can operate efficiently on individual devices. Current estimates suggest data centers will consume 20% of global electricity by 2025. Neuromorphic computing offers a fundamentally different approach by mimicking how the human brain processes information.
The energy efficiency gains here are staggering. Neuromorphic systems can use up to 100,000 times less power than conventional computers while performing similar tasks. The human brain operates on about 20 watts, less than a light bulb, while performing computations that would require megawatts in traditional data centers. Companies like Intel with their Loihi 2 chip, IBM's True North, and emerging players like SynSense are developing processors that only activate when needed, processing information through spikes and events rather than continuous calculations.
What makes this particularly interesting from an investment perspective is that neuromorphic computing addresses multiple constraints simultaneously: energy efficiency, real-time processing, and privacy. Edge AI devices powered by neuromorphic chips can make decisions locally without sending data to cloud servers, which is crucial for applications like autonomous vehicles, medical devices, and IoT sensors. The neuromorphic computing market is projected to reach $8.3 billion by 2030, but the real opportunity may be in the applications it enables rather than the chips themselves.
This connects to our fourth frontier, synthetic data and simulation. One of the biggest constraints on AI development has been access to high-quality, diverse training data. Privacy regulations, data scarcity in specialized domains, and the simple cost of collecting and labeling real-world data have created bottlenecks. Synthetic data generation offers a solution by creating artificial datasets that capture the statistical properties of real data without containing actual personal information.
The synthetic data market is experiencing explosive growth, projected to expand from $2 billion in 2025 to $10 billion by 2033, representing a 25% compound annual growth rate. But the numbers only tell part of the story. Synthetic data isn't just about replacing real data, it's about creating data that never could have existed otherwise. You can generate training scenarios for autonomous vehicles that include every possible edge case, create medical data sets with perfect diversity and balance, or simulate financial market conditions that haven't occurred yet.
Think of synthetic data as the difference between learning to drive only on the roads you've personally traveled versus training in a simulator that can recreate every possible driving scenario. Different weather conditions, unexpected obstacles, various vehicle types, even scenarios that rarely occur in real life but are critical for safety. Recent breakthroughs in generative AI, particularly with GANs and diffusion models, are producing synthetic data so realistic that it's often indistinguishable from authentic data, while being guaranteed to be privacy-preserving.
Our fifth investment frontier brings us to neurosymbolic AI, which represents a fundamental rethinking of how AI systems should be architected. Current large language models are impressive pattern recognition systems, but they struggle with logical reasoning, consistency, and explainability.
I like to think of this as combining intuition with logic. Neural networks are excellent at intuitive pattern recognition, looking at an image and immediately knowing it contains a cat. But they struggle with logical chains of reasoning. If A implies B and B implies C, then A must imply C. Neurosymbolic AI aims to get the best of both approaches.
What's particularly exciting for investors is that neurosymbolic systems address the black box problem that has limited AI adoption in critical applications. When an AI system makes a decision about loan approval, medical diagnosis, or legal judgment, stakeholders need to understand the reasoning process. Neurosymbolic systems can provide clear explanations for their decisions by showing the logical steps and rules that led to specific conclusions. Recent research shows that neurosymbolic architectures, particularly what's called the neurosymbolic neuromodel, consistently outperform pure neural approaches across multiple evaluation metrics. These systems can handle both learned patterns and explicit knowledge, making them particularly valuable for applications that require both adaptability and reliability. Think medical diagnosis systems that can learn from new research while following established medical protocols.
Our final investment frontier is perhaps the most crucial: safety, evaluation, and alignment. As AI systems become more powerful and autonomous, the need for robust safety frameworks becomes existential rather than optional. We're seeing increased funding for third-party audits, expanding benchmark systems, and shared research findings across the industry.
The 2025 AI Safety Index, which evaluates leading AI companies on 33 indicators of responsible development, shows both progress and gaps in the industry. Companies like OpenAI, Anthropic, and Google DeepMind are investing heavily in safety research, but significant challenges remain. The development of comprehensive evaluation frameworks, benchmarks that can assess not just what AI systems can do, but what they might do under adversarial conditions, has become a critical infrastructure need.
What's changed is the recognition that safety isn't just about preventing obvious harms, but about ensuring AI systems remain aligned with human values as they become more capable. Andrew Ng has emphasized the importance of agentic AI, systems that can autonomously plan and execute complex tasks, but he's also highlighted that such systems require careful oversight and persistent memory systems to ensure they remain under human control. The investment opportunity here isn't just in safety research, but in the entire infrastructure of AI governance: evaluation tools, monitoring systems, audit frameworks, and alignment research. As regulations like the EU AI Act create mandatory safety requirements, companies that can provide reliable safety solutions will find themselves in high demand. It's similar to how the growth of the internet created massive opportunities in cybersecurity. AI safety could be an even larger market.
Let's turn to what industry leaders are saying about these frontiers. Andrew Ng, often called the godfather of modern AI, has been particularly vocal about the shift toward agentic AI. His perspective is that most enterprises should focus on building applications using agentic workflows rather than chasing the most powerful foundational models. He argues that GPT 3.5 with proper agentic architecture can outperform GPT-4 in many real-world applications.
Nang's insight here is profound. It's not just about having more powerful models, but about how we orchestrate them. Agentic workflows allow AI systems to plan, execute, review, and refine their work, much like human problem-solving. This iterative approach often produces better results than trying to solve complex problems in a single forward pass. For investors, this suggests that the value will increasingly be in the orchestration layer, the systems that coordinate multiple AI models and tools, rather than just in the models themselves.
Satya Nadella at Microsoft has been focused on addressing what he calls the unintended consequences of AI deployment. His perspective is that the industry needs to be proactive about managing risks rather than reactive. Microsoft's approach has been to integrate safety and oversight mechanisms directly into their AI products from the beginning, rather than treating safety as an afterthought.
Nadella's philosophy represents a shift in how large tech companies think about AI development. Rather than the traditional move fast and break things approach, we're seeing more emphasis on move fast and build things responsibly. This creates opportunities for companies that can provide safety by design solutions, tools and frameworks that make it easier to build AI systems that are secure, transparent, and aligned with human values from the ground up.
Jensen Huang at NVIDIA has been promoting what he calls the ubiquity of AI PCs, the idea that every personal computer will soon have significant AI capabilities built directly into the hardware. NVIDIA's new RTX 50 series GPUs and their AI foundation models represent a bet that AI will become as fundamental to computing as graphics processing was to gaming.
Huang's vision extends beyond just more powerful hardware. He's describing a future where every computer becomes an AI assistant, capable of understanding natural language, generating content, and helping with complex tasks. The recent announcement of Project Digits, which brings NVIDIA's Grace Blackwell architecture to developer desktops, suggests they're betting on distributed AI processing rather than centralized cloud computing for many applications.
Meanwhile, EU regulators are emphasizing societal benefit and transparency in AI development. The AI Act, which came into effect in 2024, requires high-risk AI systems to meet strict transparency and accountability standards. This regulatory framework is creating a bifurcated market where AI companies must choose between maximum performance and regulatory compliance.
But this regulatory pressure is also creating opportunities. Companies that can build AI systems that are both powerful and compliant with evolving regulations will have significant competitive advantages. It's similar to how environmental regulations initially seemed like constraints on business, but ultimately created entire new industries around clean technology and sustainable practices.
Looking at the broader investment landscape, we're seeing a shift from infrastructure investments toward application layer solutions. The first wave of AI investment focused on building the foundational capabilities, larger models, faster chips, more data centers. But as those capabilities mature, the value is increasingly moving toward companies that can apply AI to solve specific real-world problems.
This shift is reflected in the funding patterns we're seeing. While total AI funding remains strong, investors are becoming more focused on companies that can demonstrate clear paths to profitability and real-world impact. The days of funding AI companies based purely on technical capability are giving way to more traditional metrics: revenue growth, market penetration, and sustainable competitive advantages.
The geopolitical dimension adds another layer of complexity to these investment decisions. Different regions are making different bets about which technological approaches will prove most valuable. China is investing heavily in neuromorphic computing and embodied AI. The United States is focusing on foundation models and safety research, while Europe is emphasizing regulatory frameworks and ethical AI development.
These regional differences create both opportunities and risks for investors. Companies that can navigate multiple regulatory environments and cultural expectations will have access to larger markets. But the complexity of compliance across different jurisdictions is also increasing. We're likely to see more regionalization in AI development, with different technology stacks optimized for different regulatory and cultural contexts.
One particularly interesting trend is the convergence of these different investment frontiers. World models enable better robotics. Neuromorphic computing makes edge AI more practical. Synthetic data solves training problems across multiple domains. And neurosymbolic approaches provide the reasoning capabilities needed for safe, autonomous systems. The companies that can integrate across these different areas may have the strongest competitive positions.
It's like watching the formation of a new technological ecosystem. Just as the internet brought together networking, computing, and content creation into a unified platform, these AI investment frontiers are creating the foundation for what we might call the intelligent infrastructure of the future. Systems that can perceive, reason, learn, and act in the physical world while remaining safe and aligned with human values.
The timeline for these developments is accelerating rapidly. Many experts believe we could see significant breakthroughs in world models, embodied AI, and neuromorphic computing within the next 2 to 3 years. The synthetic data market is already experiencing explosive growth, and neurosymbolic approaches are moving from research labs into commercial applications.
But perhaps the most important insight for investors is that these aren't just technological bets. They represent fundamental shifts in how we think about intelligence, computation, and the relationship between humans and machines. The companies that successfully navigate these transitions won't just be building better AI systems, they'll be creating the tools and platforms that define how intelligence is deployed in the world for decades to come.
As we wrap up this final episode of State of the AI Industry 2025, it's worth reflecting on the journey we've taken together. We started by examining the foundational hardware that powers AI, the GPUs, TPUs, and specialized chips that modern AI possible. We explored the AI labs where breakthrough models are developed, the cloud infrastructure that scales these systems globally, and the diverse applications transforming every industry.
We've seen how the AI supply chain creates complex interdependencies between hardware manufacturers, cloud providers, model developers, and application builders. We've examined how different business models, from API services to embedded solutions, are competing for market share. And we've tracked the geopolitical forces that are reshaping how AI technology is developed, deployed, and regulated around the world.
Now, as we look toward the investment frontiers that will define the next phase of AI development, we can see how all these elements are converging. The hardware advances we discussed early in the series are enabling the world models and embodied AI systems we've explored today. The cloud infrastructure provides the training environments for synthetic data generation. The regulatory frameworks are creating the market conditions for safety and alignment research.
What emerges is a picture of an industry that's moving beyond the pure scaling phase, just building bigger and more powerful systems, toward a more nuanced understanding of how AI can be integrated into the fabric of society. The investment frontiers we've discussed today represent bets on specific visions of that future. AI that understands the physical world, robots that work alongside humans, computing that mimics biological efficiency, data that preserves privacy while enabling learning, reasoning systems that are both powerful and explainable, and safety frameworks that ensure AI remains beneficial as it becomes more capable.
For listeners who want to stay ahead in this rapidly evolving landscape, the key insight is that the AI industry is becoming more specialized and more integrated simultaneously. Success will increasingly depend on understanding not just individual technologies, but how they fit together into larger systems and how they interact with regulatory, economic, and social forces.
The next few years will likely determine which of these investment frontiers prove most valuable and which companies successfully navigate the transition from the current generation of AI to whatever comes next. It's an incredibly exciting time to be following this industry, and we've been honored to share this journey with you throughout this series.
Thank you for joining us for State of the AI Industry 2025. Whether you're an investor, entrepreneur, researcher, or simply someone trying to understand how AI will shape our future, we hope this series has provided valuable insights into one of the most transformative technological developments of our time. The future of artificial intelligence is being written right now, and understanding these investment frontiers will be crucial for anyone who wants to be part of that story.
Until next time, keep watching the horizon. In AI, what seems like science fiction today often becomes commercial reality tomorrow, and the companies that can spot those transitions first will be the ones that define the industry's future.